And I'm really delighted to introduce our next speaker, Dr. John Smee, who's Vice President of Engineering at Qualcomm Technologies. And he's been at Qualcomm since 2000 and has been involved in a lot of the work in wireless communication systems. And right now he is the 5G R&D lead, responsible for leading all of the 5G research projects. Dr. Smee received his PhD from Princeton University, also an MA from Princeton, and MS and BS from Queen's University. So let's welcome Dr. Smee.
All right, well, thank you very much. It's always my pleasure to come to this Texas Wireless Summit and also see all our good friends from UT Austin. So seeing Jeff Andrews in the crowd and many others, it's really awesome to kind of come here and talk to you about, where 5G is going next. And obviously, I know a lot of interesting discussion as well. What's the timeline for 6G? How's that going to fit into 5G evolution? So I'll hope to cover a few of those topics this afternoon. And kind of jumping right in, what's interesting is how fast 5G commercialization has happened. If we look back 5 years ago, there was a lot of questions of, is there really a desire for 5G? We're living in a gigabit LTE world. So the question is, well, what's happening in this spectrum? What's happening in the operator ecosystem, the health of the infrastructure vendors, the operators, the whole mobile ecosystem? And the reality is that even much faster than 4G, 5G rollouts are already happening. So we see that both in the sub-7 gigahertz bands and then also millimeter wave bands like 28 gigahertz and 39 gigahertz. You see those starting to roll out not only in the United States, but also in Europe and Russia. And it's also something where we know before too long we'll start seeing a lot more millimeter wave deployments in countries like Korea and Japan as well. And so if you look at what's really happening with 5G and what's the broad vision, and I think it's interesting to look at public networks and private networks, and it's really not this simple thing that 5G is about just adding more frequency bands to your existing cell network. It's really also a lot of change in topology. So how the network gets deployed, how expensive it is to deploy, how do technologies like relay and integrated access and backhaul fit into the system? And then also we have to look at the use cases across what's going to happen in, for example, stadiums. When there's large numbers of people, that's often when the data demands are highest on the system, both downlink and uplink. And then also taking 5G into factories beyond consumer markets and indoor enterprises as well. If we look at the data rates that are possible on unlicensed spectrum and the fact that 5G is working on unlicensed and licensed spectrum, all of a sudden the amount of data you can get in a 5G private network is very high. So a lot of these different use cases are coming together, and then we have this reality of the standardization timeline of how we're moving through that cycle. And so a good way to think of that is that release 15 is what was the first work item that's already finished. That's what those products that are out there today are using release 15. Release 14 was a big study item. That's when we were debating a lot of things, whether it's waveforms and coding. Those things were really being discussed in the release 14 study item. Well, release 15 was the work item that made the first spec. And then release 16 is almost finished, a couple more months to go, and that's going to be this expansion that's already happening in release 16. And by way of timeline, we can think of LTE having released 8, 9, 10, 11, 12, 13 before release 14. So you can think of, is there going to be 6 or 7 releases of 5G? Well, maybe. And the question is, how is it going to evolve into release 17 and beyond? And so one of them is the commercial deployment reality of the new use cases getting addressed. And the other thing is, how is the system actually getting more efficient? So the air interface is really continuing to evolve. And so a company like Qualcomm, we have a lot of systems engineers doing wireless systems design, evaluation on the network side, on the link side, on the prototype side, pushing the designs of 5G. And it's partly also because we're trying to say, hey, let's feed that roadmap that's going to drive this continued evolution and expansion. And another thing is when you look at the smartphone business, as Brian Modoff was mentioning earlier this morning, there's this huge explosion of opportunity beyond just the mobile smartphone. And so we can look at the aspect of how is 5G moving into augmented reality, how is it moving into factories. And there's one of the exciting things at this juncture of 5G is the number of industries who are really rolling up their sleeves and trying to figure out proactively, what does 5G mean for them? How can they leverage 5G for their own particular use case needs? And so that's examples of industrial IoT, or even examples like private networks, or augmented reality and virtual reality. So all of these technologies are looking at the capabilities of 5G and saying, well, I can actually change my product, I can change my design. Things like NR Lite, taking 5G in release 17 into sensors. And we saw very interesting talks this morning on the sensor market. And so even though LTE evolution with eMTC and NB-IoT can address low power wide area, in 5G there's also a desire to take that into a more mid-tier data rate and coverage scenario. And so you're seeing this proliferation of IoT, not only for industrial, but also for consumer applications. And this is also an interesting one to talk about here in Austin, because I know there was a lot of discussion at TWS when I was here maybe 5 or 6 years ago about fixed wireless and even millimeter wave bands and the notion of the reflection and the diffraction and the propagation. And this is a very interesting use case because it also introduces some competition into the home broadband market, not only the consumer mobile market, but the home broadband market. So the ability to leverage the high data rates, wide bandwidth, fixed deployments, you can be using both like outdoor placement of CPEs or indoor placements, and then all of a sudden the fact that you have this beamforming at millimeter wave enables that very wide bandwidth to translate into very high data rates into these home use applications. And so this is an example of something where it also gets into the pricing plans of the overall data, what's a smartphone plan, what's a home plan. And so for all of us as consumers, it's just interesting to think about that notion of you're designing and deploying a 5G network, what's also serving this mixture of fixed and mobile. And then even from the transmit power standpoint, from an engineering perspective, a link budget, EIRP, this is something where what's the actual transmit power capabilities you can get out of different modules. So for Qualcomm, having a product line that's focused on also making sure we're getting very high performance uplink and downlink data rates and capacity and coverage. So it's an interesting reality of as we saw a lot of interest in the fixed broadband market several years ago, that this is now part of this, even these release 15 deployments and technology evolution happening now. And so the other thing then is, where is wireless going in terms of indoor, outdoor, enterprise? So we do like to specifically call out these indoor, outdoor venues. Like if anyone's been to a large stadium recently, and the amount of data that's created and consumed, if you were to kind of drop a sphere around that stadium, there's a huge amount of activity, whether it's people recording the game or people are broadcasting what they're seeing or people are downloading stuff to their device. And you're saying, well, what's the best way to lay out that network? What's the best way to leverage different bands together? And so it's just an interesting thing that as we're looking at 5G evolution and we're looking at the bandwidths capable in millimeter wave and in sub-6 and in unlicensed spectrum, then all of a sudden these different technologies work together to solve these different use cases. And so if we look then at the standards timeline and what's in release 16 as opposed to release 15. So release 15 is really this inner circle. And you can think of things like automotive, laptops, fixed wireless access, devices like tethered augmented reality, where you can have a headset that's USB connected to a 5G enabled smartphone. And we look at, okay, well, what's happening in release 16 and 17? So right now, even taking 5G into private networks, doing things like massive IoT, broadcast, and then also topology evolution. So I know UT Austin in particular has always done a lot of very interesting research on the topology of heterogeneous networks. Well, that's core to how 5G is going to be cost effective. So when does it make sense to use an outdoor small cell? When does it make sense to do a picocell? When does it make sense to do an indoor small cell? What's the different frequency bands being used in terms of macro versus lower height, lower power? And all these things work together to deliver that mixture of capacity, coverage, reliability, and latency. And so that's interesting reality of we're seeing this evolution happening in something like release 16, where there's been a huge focus on things like integrated access and backhaul, where base stations not only talking to devices, but also talking to other base stations when you're leveraging the fact that you're not always going to have a Ethernet backhaul link. And then technologies like industrial IoT, where the very high reliability, low latency requirement is what makes the use case unique. So we're all familiar with things like hybrid ARQ, so that introduces reliability with some latency hit. So what's the best way to design a 5G hybrid ARQ system that also across the protocol stack has the end-to-end latency needed for these particular applications? And again, as Brian mentioned this morning, it's this aspect of you're going to be replacing Ethernet in many of these scenarios. So the reliability and the latency really have to be achieved. And so you look into the coverage capacity and when are multiple antennas working together in terms of the density of the network, things like COMP, like coordinated multipoint. That was researched in release 10 of LTE, but it's also core to how to achieve reliability in a semi-planned network. So we're putting these antenna sites closer to each other because we're trying to drive this very high level of reliability, and at the same time, we're trying to make this high capacity, high coverage combination. And augmented reality is a great example where it kind of brings together not only the compute side, but the communication side. So it's something interesting to think about when we look at, the smartphone actually came after LTE was already, standardized. After there was the initial release 8 in 2009, 2010, we started seeing smartphones come after that. Well, it's that same question, where will augmented reality be in 5 years, and how much of that will leverage the underpinnings of 5G in terms of the data rate, the capacity, the coverage, the focus on energy efficiency. So I think it's a really interesting cross technology device because it leverages all these unique capabilities and it puts them at the forefront of the challenge. So we're pushing multimedia in terms of the amount of visual processing we need to have in the devices. It's also pushing in terms of the low power RF and baseband. And then it's also splitting this notion of what's happening on the device versus in the network. So we're familiar with what's happening in the cloud, but we like to think, okay, what's happening in the edge cloud when latency matters more? And so that's one of the exciting areas of pushing augmented reality and virtual reality in terms of pushing those boundaries. And so this is the aspect then of this intelligent edge. So if we look at augmented reality and we look at artificial intelligence, so this notion of what's happening and where it's happening, the role of privacy and security and efficiency, then one of the interesting things for Qualcomm, we're obviously looking at, hey, what's the right thing to do on device? So we have a lot of on-device AI, but at the same time, how does that complement the AI that's in the cloud? And so again, this question of what's the functionality, how does it get distributed? So one of the things that we're researching and investigating and looking at the deployment for is this aspect of what's the best spot to actually implement various aspects of the inference, of the actual training of the neural networks, and then how does it map to these end-to-end use cases? So if you're putting 5G in a private network, what intelligence and what data are you going to store at the factory, very sensitive information, versus what are you going to put in a cloud? And then the other thing is in the factory, the different devices that are communicating, whether it's an AGV or a robot or a handheld, what's happening on that device versus in a local server within those premises. So for each of the different use cases, there's a slightly different split that might be the most cost-effective. And then the question is, from the engineering standpoint, what's the way to bring these things together in the right way? And so it's very exciting where we have a mixture of machine learning researchers who are not only looking at machine learning applied to wireless, but then also machine learning applied to multimedia, and then machine learning applied to cloud inference versus inference on the device. And so one thing we all know is that the network itself is getting smarter and smarter, and we want to leverage that intelligence to have more optimized scheduling algorithms, more optimized QoS. If we look at the efficiency and the fact that the deployments, we want to make them less, hand-tuned. So the self-tuning and the self-planning of the network, that's one of the cost savings you can get as you're starting to leverage that big data on the network side. And then the other thing is then the end-to-end system. So we kind of call it radio awareness. So anyone who's worked in wireless for any period of time knows the amount of attention that gets paid into channel estimation, channel prediction, scheduling, MIMO, rank prediction, CQI, and that aspect of link adaptation. So if only you could better predict the channel, you could more efficiently use it. And it's not just about a point-to-point optimization, it's really about the multi-user interference environment you're creating. So every transmission between a base station and a device obviously can be recipient to another device as well. So how do we optimize then the net trade-off of delivered power and the unwanted interference? And so that's that aspect then of the machine learning being able to better train on these evolving data sets. And so you can think of this accumulation of knowledge, and as that gets more distributed and you're starting to accumulate more and more of it, then all of a sudden the sophistication of the algorithms, you start abstracting away from a more specific model of the channel. You don't need to parameterize everything because the system, you can abstract it to a higher level where the scheduling is actually trying to optimize a particular overall network efficiency. And so it's one of those aspects that as we look at AI, there's the simplistic network side aspect, and then there's also this end-to-end aspect of how do we even do spectrum. So a lot of focus on licensed spectrum, unlicensed spectrum, and then shared spectrum. So as we know that if we look at cellular network efficiency, the figure of merit of bits per second per hertz is all about efficiently using the spectrum. And so what's the right way to leverage that to have more proper spectrum sensing? So we saw this morning the role of multiple microphones to better understand a kind of auditory environment. Well, that same thing, if we look at large distributed sensor grids, listening to the RF environment, then all of a sudden that map of interference and the map of delivered signal becomes an input to the overall optimization. So as we look longer term at what's next for wireless, bringing things like artificial intelligence and machine learning with low power sensor and the right amount of feedback, combined with a more intelligent decision of what's happening where in the network, is what puts these different things together. So this is just a good example of a factory of the future, where we look at what's the information flow being created within this factory. And you look at AGVs on the floor, or handheld terminals, or an industrial robot. And then we look at system engineers, we say, hey, okay, we understand our use cases of mobile broadband, of high data rate to a phone. We understand massive IoT of low power sensors, and we understand ultra reliable, low latency communication. So the interesting thing is within this given fabric of this factory, we actually have examples from each of these three pillars. And so then how do you fit the overall spectrum usage together? So maybe we have 100 megahertz of spectrum at 3.7 gigahertz, which for example in Germany is a particular band that's been allocated to industrial IoT. Well, how can we use that spectrum most efficiently to serve all of these different use cases? So then all of a sudden the putting together the different requirements and the trade-offs of reliability, capacity, coverage, and latency, it's a constrained optimization. And another very important use cases, we were just talking earlier this morning with some of the spin-outs from UT Austin, like GenXCom, who's been looking at full duplex. And for Qualcomm, technologies like full duplex are kind of core to how we approach the evolution of wireless. And a good example of that is our focus on automotive communication needs. And so we talk of the notion of the cellular V2X. So it can be vehicle to vehicle, it can be vehicle to infrastructure, and it can also be vehicle to pedestrian. So with more and more, pedestrians obviously having smartphones on them, and as the cars get connected as well, then all of a sudden some interesting safety applications are worthy of research. And then the intelligence that's within the device or within the car or within the intelligent transportation fabric is also high enough that all of a sudden you can do a more optimized decision, whether it's for traffic avoidance or for safety. And you're trying to take a lot of this confusion away from the driver of the vehicle so that it's basically a more end-to-end safe transportation system. And so this is a great application for both AI and communication. And it's a question then of what's the right technique. And so we can see in release 16, there's already a lot of work to enable V2X, the foundations of what we call peer-to-peer or PC5-based communication, that is device to device. In addition to the fact that it's device to network is inherent in the 5G standard. So even as we look towards release 17, what are some further optimizations we can do for the device to pedestrian use case? What are some further optimizations in terms of side link and in terms of relays, building upon what we're already doing in integrated access and backhaul? So the V2X is a very kind of, if we look at the automotive ecosystem as a whole, it's a huge growth market on the semiconductor side, but it's also a huge application space on the wireless side. It's one of those markets where every day there's a different use case, every day the car becomes more intelligent, the amount of data that can be leveraged on the car for both efficient operation, for maintenance, and how do you put all of that different elements together? It's often going to involve the movement of this data on and off the car. So when do you want to do that? What are the size of the packets? What's the latency requirements for a particular car-to-car application versus an infrequent upload? So one of the key messages is that it's not one size fits all. So from a QoS standpoint, it's really about understanding and breaking down these different use cases, and then what are the right building blocks within the evolving 5G and R system so that we can address each of these use cases as a point-wise solution. And so then if we look at this kind of full span of what was in release 15 and what's in release 16, what's likely for release 17, so these decisions of what's the specific content of release 17 will be decided in the next month or so. And so we've been involved in many different industry discussions on that prioritization. And then the important thing is after release 17, we see a release 18, 19, 20. And so we're seeing that continued evolution of the market, not just on the smartphone, mobile broadband space, but then really also on this industrial vertical space. And that's when we look then at this longer term aspect of more disruptive approaches. One thing that's very important to keep in mind is the flexibility. If we look at network function virtualization or disaggregated RAN. So the system itself can evolve now in more complex ways. It's not about just taking out a baseband platform and putting in a new baseband platform, or taking down some antennas and putting up new antennas that do a higher frequency band. It's really about the fact that these deployments, these investments that got made on that second slide where we were showcasing those 2019 5G deployments, that investments that are being made, where the operators want that to forward evolve in a way that's cost effective, that's leveraging the money that's already spent. And so that adding capabilities to 5G is going to be a huge focus of the wireless ecosystem for the next decade, so that these investments are serving multiple use cases, whether it's the vehicle use case, whether it's the industrial IoT use case, whether it's the growing amount of what we call the handheld use case, or the NR Lite, the sensors, the wearables, this explosion of different types of IoT devices. And the other interesting thing is the continued hunt for new spectrum. So we're already doing interesting measurements in bands like 115 gigahertz. We're obviously looking at bands like 60 gigahertz for NR unlicensed. So the same way LTE was designed for licensed and unlicensed spectrum with LTEU and LAA, well, 5G is being designed for licensed and unlicensed spectrum already in release 16 for the sub 7 gigahertz bands, but then taking unlicensed spectrum into bands like 60 gigahertz for a 5G system-based deployment is another example of an active area of research. And then the other big question is, well, what's the right frequency band as we're doing things like positioning? So we look at a lot of these use cases, whether it's augmented reality or an AGV in a factory, we need to know the accurate location of a device. And we also want to predict the path planning, whether it's a vehicular application or an in-building application. And so you start to think about spectrum and what's the right signals we would embed within those waveforms to do accurate position measurements, given that those signals are already pretty wideband. Many of the bands in 5G are 100 megahertz wide component carriers. It's even possible to do 400 megahertz wide component carriers. So the level of accuracy we can get is getting higher and higher in 5G. So then the question of using spectrum for positioning, for ranging, in addition for communication, becomes part of how we solve these more complex use cases. And so as we look towards the second half of 5G and the integration of things like artificial intelligence and bringing in a more optimized end-to-end system, then that's where we're going to start looking, okay, what are the benefits then of at what point we'd move to a 6G platform where we say, hey, let's take another fresh sheet of paper and let's look at how we would assemble the technologies in a 2030 timeframe in a slightly different way. But in the meantime, there's a second half of 5G that's coming after release 17 that'll keep focusing on evolving this footprint that's getting deployed as we speak. So I'm certainly happy to take any questions, and thanks very much.
Okay, the microphones are open.
Hi. So at the very end there, you were talking about this blank sheet of paper for 6G. And one of my questions was, for the communities who can afford to advance their technology and update every 10 years, this is great. But what are we doing for the communities who can't upgrade, low-income communities and other places around the world where they can't upgrade their technology and their systems, especially at a city infrastructure way, every 10 years, that's...
Absolutely.
Is there anything that's happening to help them?
Yeah, and I think that's the overall, whether it's a city plan or a state plan or a federal plan, as people are looking at, what's the time frame of what replacement cycle, if you will. So no one's, even today, they're not ripping out 4G to put in 5G. And so in terms of, many markets in the world haven't even significantly deployed 4G. So those markets will be able to leverage the, economies of scale of markets that have already been developed elsewhere. And if we look and then on the policy side of connectivity across different regions, then that's more of a policy question of what's the right way to incentivize operator deployments that are going to cover those markets. And I think we're already seeing that play out today, that operators are focused on that, if they're looking at the footprint of their coverage and the number of population that is served with a smartphone. And we look at the cost of deployment. One of the core parts about evolving technologies and even this terminology of disaggregated RAN is to make the system less expensive to deploy. And then you're starting to leverage then this mixture of this evolution of the prior G with some new technologies being served on the new G. But I think it's a good question.
Okay, we have room for one more question.
You said release 16 will future-proof 5G. Can you explain that? That's a strong statement.
Yeah, so what we mean is that if release 15, so if we looked at the deployment challenges of release 15, what we knew was that we needed those building blocks. So if someone deploys, say, 100 megahertz at 3.7 gigahertz, based on release 15, that we want to make sure that it's forward compatible to what's coming in release 16, 17, 18. So if there's a release 15 device, it can continue to live in that network. And so I know, Jeff, you know this well, but if we looked at, say, in LTE, there was almost blank subframes. And so we looked at the spectral occupancy as a function of time, and what is a new device going to be expecting to be transmitted. So part of the flexible framework of 5G that was instantiated in release 15 was you actually have a lot less guaranteed transmission, such that there's more freedom to add other stuff later. So even the kind of protocols of what's expected, the base stations are not radiating at 3 in the morning, 20% of their power on a pilot. Instead, the system is more responsive inherently in terms of the transmission protocol between the network and the device. And so that future-proof is really meaning the fact that we can bring in other evolutionary capabilities in a way that doesn't displace the original, devices that are out there. But it gives an operator who's deployed release 15 a path to add substantially different use cases in the future. And that's why things like V2X, things like broadcast, things like ultra-reliable low-latency communication can all happen on the same carrier. It's because that time frequency grid in 5G is more adaptable than it was in 4G.
All right, let's thank our speaker again. Thank you so much. Okay. Next, we have Dr. Gabe Cohn, who is at Microsoft Research. He's working at a Microsoft healthcare division, working on sensing technologies, targeting applications in the space of health and well-being. Dr. Cohn has received a BS in electrical engineering from Caltech and a PhD also in electrical engineering from the University of Washington. And I should also say that his work on his PhD, which was on ultra-low power sensing networks, led to a startup that he successfully sold to Sears. And so he's done a lot of tremendous work in pioneering how we can leverage different kinds of signals towards human-centered applications, and I'm sure we're going to hear more about that right now. So with that, go ahead, Gabe. Thank you.
Mic working? Can you guys hear me? All right.
Let's see if we maybe press the button there.
Can you hear me now? Yes. All right,
Perfect.
so you have to push the button that says push. All right, so thanks for the introduction. Again, my name is Gabe Cohn. I'm currently a researcher in the Health Futures group at Microsoft Research, where I work primarily on developing new medical devices for cardiovascular health. I'm not actually going to talk about that at all in this talk, but if you want to talk about that, find me at the break. What I am going to talk about today is some of the work that I did along with some of my colleagues in the past on redefining noise. So first, what is noise? I think a lot of us in the room have an intuitive sense of what signals are noise. But effectively, it's an unwanted signal, something that degrades the useful information that we're trying to extract. But oftentimes, there's actually information embedded in signals that we consider noise, and that's what this talk is about, is looking at things that we consider noise and reclassifying them as signal. So first, I'm going to start with an example from radio astronomy. Little known fact about me is actually, as an undergrad, I did about 3 summers of research in radio astronomy before I decided I didn't want to have anything to do with that anymore. This story is actually about long before I was born. 1964, 2 engineers from Bell Labs were experimenting with this super sensitive 6-meter horn, and they were trying to classify all the sources of noise in the system. And even after they accounted for everything that they could think of, there was still about 3 to 4 Kelvin of noise they couldn't explain. And wherever they pointed the antenna in the sky, they still saw this noise. Now, of course, now we understand this. This is known as the cosmic microwave background. And it turns out it's not actually uniform across the entire sky. This picture is a map of that noise as a function of angle in the sky. And there's a lot of useful information embedded in this cosmic microwave background. It's actually enabled us to confirm the Big Bang Theory, determine the age of the universe, the flatness of the universe, the expansion of the universe, and many other important discoveries in cosmology. So the takeaway here is that sometimes things that we consider noise that we just want to get rid of actually have really useful information in them. And that's what this talk's about. I'm not going to talk more about radio astronomy or the cosmic microwave background. I'm going to talk about electromagnetic interference, EMI. So this is the noise generated from the electrical devices all around us. So this can be conducted noise that ends up on the power lines, or radiated noise that gets radiated off into the air around us. So what does this noise look like? I'm going to do a demo. This is an easy demo. You can do it at home. All you need is an antenna. I'm going to use an audio cable, a way to digitize it. I have a USB sound card, and a way to view it. So I'm going to use this SigView software that I downloaded. Let's see. The thing with live demos is you never know what's going to happen. But I have confidence that there will be noise here, because there's noise everywhere. All right, let's see here. Okay, except that you can't really see these graphs. All right, let me resize it back over here. There's always a resolution problem. All right, somehow they just disappeared. That's great. And I thought this would be an easy demo, right? There's no easy demos. Okay, let's try this again. It's close. All right, so you see nothing right now. That's expected. That's because I'm using this audio cable, which is shielded by design to not pick up radiated EMI. So I'm going to extend the antenna to include myself. I'm just going to touch the end of it. And you still see nothing. Great. And I was told everything's bigger in Texas. All right, so let's see what's going on. Why can I not see? All right, there is some very weak noise. Let's just scale this a little bit. All right, so there's some really, really weak 60 hertz noise. And I've never seen it so weak. I will make it much larger by grabbing the power cord into my laptop. There we go. So you'll see mostly 60 hertz and harmonics. If you want to see it go crazy, I'll grab the power brick. There you go, lots of noise. This is the kind of noise I'm talking about. So I'll dig into this in a little bit more detail in the coming slides. There's a lot of problems with this setup, yeah. But the idea was it was supposed to show you, look how easy it is to get noise. I guess I failed in that. All right, back to the slides. Okay, so what do we use this noise for? I'm going to show some applications in activity recognition using both the conducted EMI and the radiated EMI for energy monitoring and gesture recognition. And there's a whole bunch of pieces of work I'm going to go through. I'm going to kind of do this at lightning pace really fast, but hopefully I can just show you just a glimpse at each of them. And then I'll take a step back and try to generalize the methods for finding signal in signals that we usually consider as noise, so you can apply it to other domains of research and other applications. All right, so first let's look at using conducted EMI for energy monitoring. So as I mentioned, noise that's generated by the electronics all around us is conducted onto the power lines. Initially, when this work began, actually way back when I was still an undergrad, not by me, they were looking just at resistive and inductive loads, and the noise that's generated when the user flips the switch on and off. So when a user flips the switch on and off, you can kind of see there's these peaks in these graphs here. That's the transient noise that's generated when the switch is flipped. And the signature and the frequency domain of that noise is actually consistent for that switch every time that it's fired. And so by basically monitoring the power line with a single sensor, which just does some filtering and takes some FFTs, anywhere on the power line, you can have a sensor plugged in at any point, and you can see the signature generated by each device all over the house. So every time you flip a switch on, some noise is generated. And based on the frequency content of that noise, you can classify which switch was flipped. So using that, you can tell when devices are turned on and off. Of course, that only works for these resistive and inductive loads, which tend to be some of the larger consumers of energy in the home, but not the most common. Nowadays, we have lots of consumer electronics that use switch mode power supplies. So luckily, inside the switch mode power supply, inside the power supply, there's also a switching mechanism in order to generate the DC. And this switch is much faster, right? This is switching at tens to hundreds of kilohertz, and so it's generating continuous noise on the power line whenever it's on. So here's a spectrogram of what that noise looks like. We have frequency on the x-axis, time on the y-axis. This line going all the way through is a PC that's on throughout this measurement. Here you can see when a laptop gets unplugged and its supply disappears. Here's a TV that's getting turned on, and here's a lamp that's turned on momentarily. This was all measured from, again, the same single point sensor at one point on the power line, and can see the noise generated by appliances all over the home. And each of those devices, again, is unique. In this case, in the continuous noise and the frequency, bandwidth, and amplitude of the noise it generates. And again, these signatures are stable over time. So using this type of thing, you can figure out what appliances are being used at all times in the home, and then you could, instead of getting at the end of the month, for example, an aggregate bill, this is how much energy you spent, here's how much energy went to your TV, here's how much energy went to your dishwasher, and so on. So that's just a brief look at what you can do with conducted EMI for energy monitoring. You can also use the same conducted EMI for some gesture recognition. So let's look at another one of these noise sources. These are compact fluorescent light bulbs. They actually appeared in the plot that I showed earlier. That's a CFL lamp being turned on for a few seconds. Now, if we look more closely at the noise generated from that CFL, in this spectrogram, which has a completely different scale in both directions, the red lines that go all the way from top to bottom are the noise generated from that CFL anytime it's on. And this noise you see only when the user touches the bulb. Now, it seems like a weird thing to do, touch the bulb. Just stick with me for a minute. When you touch the bulb, you see some noise. Now, why is that happening? So if you look at the circuitry inside the CFL, there's some control circuit that's it's an oscillator. And part of this resonant circuit is the bulb, the lamp itself, right? The gas-filled lamp. So that forms a resonant circuit, and when the user brings their hand near or actually touches the bulb, they're going to capacitively load this resonance loop, and they're going to detune the oscillator. So they either cause a slight change in frequency, or more often, they just cause an increase in power consumption. And that increase in power consumption, or sometimes change in frequency, we can see in the EMI and the power lines. So here you can see a user touching a bulb with 1 finger versus 3 fingers. And as you'd expect, higher capacitive load of 3 fingers, we see more EMI in the power lines. So touching bulbs is probably not the most useful thing in the world. But you can also, if you have a bunch of overhead lamps, you can get, you're also going to capacitively load it when you walk underneath the lamp. So you can get some coarse proximity information about users moving around in a space without adding any additional instrumentation to the space. So you're using commodity CFLs, there's no instrumentation on the user, and of course you can monitor the noise generated from all those different CFLs with a single point sensor. So that's an example of doing gesture recognition using conducted EMI. Another is this project UTouch, which looks at a different appliance that generates noise, and that is an LCD. So again, if we look at that noise, the red line that goes all the way top to bottom is noise produced whenever the LCD is on, and this is the time when the user is touching the display. So what's going on here? It's actually a little bit different than the CFL, but it's similar. So an LCD, as many of you know, is just a grid, an array of pixels, and the rows of the LCD get driven sequentially. And so energy is consumed at that row rate, which produces EMI on the power line at the row rate. Again, when your hand comes near or touches the display, you're going to capacitively load the row lines, and thus higher power consumption is seen when it drives that row. And so at the row rate, you're going to see increased EMI on the power line. So this enables touch sensing on all LCDs, not just touch LCDs. Now, it's not the same. We can't tell you where you're touching. I can just tell you are touching or you're not. So it's not the most useful thing, at least not in the same way. I mean, now touch screens have become pretty ubiquitous. At the time, touch screens were like brand new, so this was like, ooh, cool. But the idea is, again, using just this noise on the power line, and again, a single point sensor, you can turn all these screens into user inputs. So now I'm going to transition a little bit from conducted EMI to radiated EMI, but still look at gesture recognition. So this should be a little bit familiar briefly, because I did a demo earlier. So that's what I was looking at, was radiated EMI. So this is the noise that's coming off of the power lines. There aren't a lot of them around here, but coming off the power lines and appliances all around us. And as you saw in the demo, they can be picked up by the human body. To sense them is easy. You just need contact to the body and a way to digitize the signal. The signals are what we saw in the demo, so you'll see primarily 60 hertz and harmonics. The amplitude of 60 hertz and harmonics is mostly a function of how close you are to the radiating source, the nearest power line typically. And that changes as you move around, as you change your posture, so it gives us some sense of the user's posture. What you didn't see in the demo, because I didn't zoom out far enough in frequency, is there's also a bunch of higher frequency peaks. These are typically the noise generated by switch mode power supplies that I talked about before on conducted EMI. And the amplitude of these peaks is a function of how close the user is to whatever appliance is generating that noise. So in a typical home or office, that gives you some idea of the user's location in the space. So you can combine these and look at them over time and actually get whole body free space gestures, just looking at noise on the body. So here's a video of this and a younger version of me. And the only instrumentation here is there's this strap around my neck. There's really no reason it has to be in my neck. That's just where I decided to connect the electrode, because it wasn't something that moved a lot. I didn't want motion artifacts. In the backpack is just a DAC that's digitizing that signal, sending it over wireless. There's no instrumentation in the environment. There's no cameras looking at me. I can do a bunch of gestures, and it recognizes the gestures I'm doing. Now, this is not a camera. It's not figuring out from the noise that I'm doing each of these gestures. There are 12 pre-trained, you can say, signatures, and it's just deciding which one is it most similar to. So it would work in constrained environments where you beforehand train, these are the gestures I want to do, and then you can do them, and as long as you don't move too much, the environment doesn't change too much, it works. But there's a lot of, it's got to be just right? We are looking at noise after all. But it does enable some sense of whole body free space gestures using just noise in the power lines that is then coupled onto the body. Now the next piece I want to look at is static E-field sensing. So if we look at more closely at the wave that we saw from the previous example, so as you can see, before and after the gesture, the high frequency noise is very different. During the gesture, there's this strange low frequency or DC offset that happens. And this is actually due to changes in the static electric field. So that is the electric field between the body and the environment. So anytime you have objects at a different potential, there'll be some electric field between them. So there's some electric field between me and the things around me. When I move, then in order to reestablish equilibrium, charge will flow to reestablish that equilibrium. So you can sense that simply by measuring the voltage between a reference plane near the body and the body itself. Whenever I move, the voltage between those 2 points is going to change. A very small amount, but it'll change. Again, to sense it is quite easy. You basically AC couple to the body, add some gain, do some filtering. You can do this in a very low power way. And you get a signal that is similar to that of an accelerometer. So in this video, the top trace is from the static E-field sensor. The lower 3 are from an accelerometer. And as I shake my wrist, you see a signal that is similar to that of an accelerometer. It's not acceleration. It can't be put into real units of motion. It can't be broken down to 3 axes of motion, but it is similar to that of the accelerometer. So the main advantage, at least when we did this work in 2012, was power. So this is actually a log scale. And you could see that the power consumption, even on this prototype device that we put together in just a week or so, is far lower than that of the best accelerometers. Again, that was 2012. Today, accelerometers have gotten a lot better. So the best research accelerometers are now on the same order of magnitude, roughly, as our research prototype of the static E-field sensor. We could get our power down, but accelerometers are always going to give you a higher fidelity signal because it's really acceleration in real units and broken down to 3 axes. So there's less of an advantage there, but another advantage that static E-field sensing has is that you can sense motion that isn't, the device itself isn't moving. So you get whole body motion. So in this video, I'm moving my leg without moving my wrist, and the device is on my wrist. You see the accelerometer traces are flat, but you still get a strong signal on the static E-field sensor. And this is because it's not really sensing motion, it's sensing changes in the capacitance between your body and the environment. And when I lift my feet, there's huge changes in my coupling to the ground. So I think this is really where it's more interesting to use is in conjunction with an accelerometer, where there's some application where you want to sense motion, you use an accelerometer, maybe you want to sense location, you use a GPS. And then the user stops moving and you want to save power, so you turn those things off and you just keep this running for a few microwatts. As soon as you see any motion, you wake up your higher fidelity sensors and use them to get location, motion, whatever it is you want. Okay, so again, that was lightning fast, but that was a bunch of applications of both energy monitoring and gesture recognition using conducted and radiated EMI. Now let me take a step back and try to generalize these methods for finding signal and noise so that you can do this and apply it to other application domains, other research areas. So how do you find signal and noise? Well, you can't search for it. That doesn't work because you're fundamentally looking at something you assume has nothing in it. It's just noise. So what you do instead is while you're doing your research, you might notice an anomalous signal. So in the case of ElectroSense, we were looking at the waveform, we had it hooked up, and someone touched the screen, and we saw something weird in the EMI. At that moment, we didn't have time to dig into it, but when we looked into it later, that was the UTouch project, where we realized that EMI is generated when you touch an LCD screen. Similarly, with human antenna, throughout that project, we saw there was this large DC waveform whenever the user moved. We didn't understand why. A couple years later, when we looked into it, we understood the static E-field sensing work. So the key is observe your surroundings closely. When you see something strange, note it. You probably won't have time in that moment to dig in and figure out what's going on, but note it, and then go back later and explore deeply to explain the phenomenon. You really can't just scratch the surface. You really do need to dig deep. And for anyone who hasn't actually been clamming for gooey ducks, this is really hard. But you do really have to dig deep to try to understand what's going on. So I'll show you a few pictures actually from the static E-field sensing exploration when you're trying to figure out what was going on. So we tried this setup on different parts of my body, in different scenarios. We were really worried about coupling to the ground, so we isolated the apparatus suspended from the ceiling, and then we isolated me suspended from the ceiling. My advisor recommended that I do these gestures naked in space, but that didn't fit into our budget, so we didn't do that. But anyway, you really have to do a lot of exploration and experimentation to figure out what's going on. And oftentimes you have to return to first principles and see if you can come up with a theoretical explanation for what's happening. Once you understand the phenomenon, you apply it to new uses. So, quick overview, you can't search for signal and noise, observe your surroundings closely, note any unexpected phenomenon, explore them more deeply to explain the phenomenon, and then apply it to new applications. And with that, I'll open it up for questions.
All right. Thank you, Gabe. This was great. Despite the issue with the wire there, I think you were able to eventually get some noise at some point. So, all right. So we have time for a question or two. All right. It's for the live streaming there, so that everybody can hear you.
So apart from the signal sensing problem, were you able to figure out a way to do localization of this signal? Let's say when you were moving your leg and the impedance was changing, is there a way to localize that, okay, the signal is changing because of the impedance change around the leg?
So let me make sure I understand the question. The question is, this is with the static E-field sensing work. Is there a way to know that it is, say, the right leg versus the left leg, or the leg versus the arm?
Exactly.
Not in an easy way. The more complicated way is if you have multiple of those sensors on the body, you can, because the amplitude and a bit of the way the wave changes is different if it's caused by basically the ground planes coupling to the environment changing versus the rest of the body. But at that point, it's far easier to use an accelerometer.
Okay. Any other questions? So I just have one for you, Gabe. So
Yeah.
this work you did maybe 5-6 years ago, and at the time, this was seminal in you being able to show that you could actually, demonstrate these kinds of gesture interaction scenarios using these signals. Now we know we can do this. So is there any other kind of signal/noise that you think would be interesting to explore for the students in the audience that might want to explore this whole space the way you did 5, 6, 7 years ago?
I don't know. I haven't thought about it in a while. I've been kind of looking at medical signals for a long time.
Hey, maybe that's one space where there might be some interesting signals, or something
it's
inside
a
the
bit
body.
more problematic to use noise in that scenario, because something that works 80% of the time is not good enough. I mean, in general, when you're looking at noise, it's not going to be perfect, right? You don't control the signal source. And whenever you don't control a signal source, you're at mercy of whatever that signal source is. So it might work a lot of the time, but it won't always work. So that's a challenge in medical. There are other domains. I can't think of any off the top of my head, but you can come talk to me later. We can brainstorm together.
Awesome. Thank you. Thanks. Dr. Cohn again. All right. Okay, so next is Michael Klug, who
Klug.
is, sorry?
Long U. Klug.
Klug
Yep.
is the corporate vice president of advanced photonics at Magic Leap. So we're very excited to have Michael here. And he's been at Magic Leap since 2014, and he leads the team developing optical components for near-eye display applications. And so what that means is those applications where you've got headsets and you need to have a display very close to your eyes. So how do you handle the optics in those contexts? So this is the work that Michael was doing. And he received a BS from MIT in 1989. And he was also at the MIT Media Lab before Joe Paradiso, who was our keynote, was actually there. Is that correct? You were there before he was?
I'm aging myself. No. Joe was over at CERN, yeah. So
All
we
right,
overlapped by
excellent.
3 years, I think.
Very good. So let's welcome Michael.
Thank you. Oh, not yet. You haven't heard anything yet. Yeah, thanks. So I think I'm the only one here who's actually trusting a wireless network with my presentation. So we're going to see how Google and the wireless and the Wi-Fi do going through this. So thank you for the introduction. Yes, I've been at Magic Leap for about 5.5, almost 6 years now. I started the Austin office. So I don't know if anybody knows that we do have an Austin office here. We have about 100 people in Austin. Probably 3/4 of them are optical and lithography and manufacturing type people. And then most of our SDK group is based here in Austin. So we're up there by Pickle Research Labs. Plenty of opportunities to interact with the local community here. So Magic Leap not only is in Austin, it's in a lot of places. It's a startup company, but we were founded in 2011. We call ourselves a startup, but we're 1,600 people, so worldwide, across probably about 10 offices spanning the globe. We kind of took this philosophy of finding the best people in the best places and not necessarily moving them all to South Florida, because not everybody wants to be there. But it's a nice place to visit. We have a lot of IP that we've developed or acquired through the course of the last 5 or 6 years, and we have a lot of support. Qualcomm, who you've heard from a number of times today, and Google were early sponsors of the company, and investors, Alibaba, Temasek, and JP Morgan, and more recently focusing on the telecoms, including AT&T, and NTT Docomo, to roll this into a 5G solution over the coming years. The kind of the intent of the company, the general intent of the company is in thinking about this concept of spatial computing, and spatial computing is an evolution and fusion of mobile devices and mobile technologies and personal computers into one wearable solution in our future. And that solution, of course, is heavily leveraging wireless technologies, including 5G, and a lot of cloud-based services as well. But to get there are a lot of elements that we need to pull together. And we start with the human. And of course, everything is about the human and the human's physical world and how the human interacts with their physical world. A communication medium is something that surrounds, enables, engages, and extends the capability of a human. And so I've represented that here by just circles. And that communication medium may include display technology. That display technology may display photons or light. It may display sound. It may display other things as well, even smell in some cases, or some kind of other sensory stimuli. There's also sensing technology. The sensing technology is sensing the physical world, and it's sensing the human as themselves. There's a service network to allow connectivity between to different humans, maybe through their media. There may be a peripheral appliance that's used for inputting data or interacting with data. There could be a cloud computing solution, computing resources, or external virtual world where that data might be stored, and that's also accessed through a service network connection. And there's a lot of compute going on in all of these places, including around the medium that the human may be wearing. And everything requires power. And that becomes a real challenge when you're trying to build something that's compact and has a lot of sensing capability and yet has to be worn and portable. We have to keep in mind that any really good media ideally does not inhibit human-to-human communication as we know it, or human-to-physical world interactions. So we should be able to see through it to the real world. We should be able to have a more or less normal interaction as well as an interaction through the medium. Oh, and by the way, of course, all of these things are generally moving with respect to one another. Oh yeah, and there's a huge variation in the physical dimensions of various humans that might be wearing these things. And one more thing, yeah, the ambient light and the temperatures can vary a lot. So there's a lot of challenges that we face when we're developing a wearable system like this that we now call spatial computer. And we took on a lot of this, of course, when we started developing Magic Leap 1. The other thing I think to think about with respect to this in terms of nomenclature is how this differs from virtual reality and augmented reality. In a virtual reality system, you're closed off and everything that you see is synthesized, and it's isolating you from the physical world on purpose. Augmented reality produces digital content that you can see through and see the real world through, but there's really no interaction between that digital content and that physical world. What spatial computing does is it really provides a platform for persistent data content that lives in the physical world. It can interact with the physical world as well as with you. So now it makes a much richer, for a much richer experience and opens up the door to a lot of other possibilities that didn't exist with just data on top of the world. So the Magic Leap 1 works with these general, three general elements here: the light wear, the light pack, and the control. The light wear is the wearable that you wear on your head. It includes the ability to produce, of course, visual information for your eyes. It's also generating light for the environment and capturing data. It's also tracking your eyes in real time, and it's providing spatialized audio, all these things in this compact unit. The light pack itself is the dedicated computer. You wear it on your belt pack, on your belt. This is where the majority of the processing occurs. It also includes biometric ID, and also is where we store a lot of data for, in terms of persistent objects in the scene. And then the 6DOF controller is a controller you hold in your hand, kind of like what some people have called air mouse. It allows you to have gesture tracking. It also has the capability to do voice recognition, and then multimodal input, so you could use it with, say, hand gestures as well. So there's 4 technology pillars that we see in creating spatial computing, and I'll go through these one by one. So live stream is capture of everything we do, both in our digital world and in our physical world, and the interactions between those two things. That data set can then be used for a variety of different applications and purposes and give feedback to the human. So that's what live stream is. Human-centered AI really captures this notion of really providing a truly human face to an artificial intelligence. And so we have a lot of work going on in that to be able to create something that is truly photorealistic down to the pores in the skin, so that when you interact with this being, I'll call it a being, that you really feel like you're interacting with a person. And the magic verse. And the magic verse is really a layer of data that permeates everything. It can permeate everything. So you can think of it as a layer of data that sits on top of the physical world and inside the physical world. And it really is, it includes many different elements. It includes GIS, it includes physical models of the buildings. It includes IoT, connected systems, world-centric artificial intelligence. All of this is included in the concept of the magic verse. So you may have a city that is the physical city that itself, the bricks and mortar. There's a digital world, on top of and kind of permeating that might include many different elements. It might include the mobility map. It might include energy and water. It might include health and fitness locations within the city, communications, entertainment, many, many other things. Also includes lots of personal magic verses. Each person can have their own magic verse. That magic verse could span an entire city, or it could be just in a single room. You could share your magic verse with others. It could be merged with others. So really the concept of magic verse is quite broad and powerful in that sense. But today I'm going to focus a little bit on sensory fields, and as you see, my background is in optics, so that's really where my strength is. I'll spend a little bit of time on some of the sensors that are, and some of the things we're doing on the system, but a little bit more time on the optics. So just to kind of go through the inventory of what's on this system, just to give you some idea, we have world cameras. We have front-facing world cameras and side-facing world cameras, and many systems that are out there have this, because we really want to maintain maximal resolution with good binocular coverage in order to use this for gesture tracking, right, for accuracy in gesture tracking, and for SLAM. The eye cameras are looking at your eyes, obviously, for a couple of different reasons. We want to be able to compute the gaze vectors to know what you're looking at. We also want to be able to see what your emotions might be, and your eyes tell a lot about your emotions. So that's something that we can sense there. And then for security, we can read your iris. Your iris is a little bit like your thumbprint in the sense that it's quite unique to you. And so we can use that to as a security feature in the system. There's a depth sensor. The depth sensor is generating structured light, which it casts out into the world across a pretty broad range. It's used for basically creating a mesh of the real world, also for sensing gesture, for reconstructing the real world, and for interleaving gesture and the world correctly so that you properly occlude elements in the real world with your gestures. There's, of course, a video camera and a picture camera, because everybody always wants to take pictures of things they're doing. However, we're very conscious of privacy, and so the system is always letting you know when there's a recording happening. There's a light on all the time. There's IMUs and magnetometers, of course, as there are in many different things to sense orientation and position. And there's a 6 degree of freedom sensor on the wearable. And that is for sensing controller orientation and controller position. The nice thing about this, it's an electromagnetic device, so it does not require line of sight. So you can have the sensor behind you, basically anywhere within arm's reach, and it will know where it's pointing and where it's positioned. So we put the sensors to use for the obvious reasons, for tracking, mapping, localization, for world reconstruction, for eye tracking, as I mentioned, and of course for hand tracking more and more. Tracking and mapping uses fairly standard approaches. Visual inertial odometry in conjunction with these persistent coordinate frames allow us to basically be able to track through large areas and come back to where we started from, and be able to use multiple systems in the same frame of reference. So a map selection, once the system is in a given environment, it will the imagery will come back from the camera. That imagery will be compared to imagery in the memory. The system will select which environment it's been in, if it recognizes the environment it's been in the past. It then estimates the pose by looking at the camera orientation relative to the imageries that it has stored. And then once it has that, it can restore the PCFs and give you accurate positioning and orientation throughout a given map. We're also doing a lot of active research on things I don't quite understand, but there's a whole group that's working on deep algorithms for SLAM and superpoint to basically decrease the latency and increase the accuracy of our systems. So meshing is important in our system for a bunch of different reasons, for identifying visual occlusions in the scene or placing them in the scene so that things look very natural. So we can place virtual objects in front of real objects. Physics-based interactions, we want to be able to have elements that move through the environment and are properly occluded from elements. We can actually play games where you can actually duck behind doorways and behind and under, behind furniture and avoid getting shot if you're playing a first-person shooter. You take it for granted until you see it happening. It's like, wait a minute, this is pretty sophisticated. And of course, environment reasoning as well to be able to place things accurately in an environment. So, the meshing happens over time. The system is worn by the user. Obviously, as the user moves around the space, the mesh is created and updated in real time. So if things move, there's sometimes a little ghost of them for a little while, and then it goes away as we update the mesh. So some of the activities that we currently have available on the device require some pre-meshing and takes a little bit of time to mesh up the room, but once you have it, it's a very nice, accurate model, and you can have a nice experience where things behave properly. There's a bunch of different ways to put information into the system. I already mentioned some of these: head pose and eye gaze. Both can be used as input. The controller, of course, and gesture. Voice, it's got voice identification as well. We have a mobile app that runs, it can run on any kind of mobile device, and of course, Bluetooth keyboard. All can be used. Hand tracking in particular is an area of focus for us recently, so a lot of improvements there. We have key point tracking with 9 points on the hand, and then about 8 different gestures that it can recognize natively. This is just a video showing some of the most recent work. And it's offset physically only because the camera is offset slightly from the digital center. So this is actually right on top of his hand. You can see how reactive it is and accurate it is in terms of the digital model on top of the physical as he rotates around. So I think we've made a lot of great progress there with the tool. Switching gears a little bit more to go into the light field itself. So one of the things that's important for Magic Leap is that we provide a physiologically correct visual scene for a number of different reasons. Biggest one is that if we don't, you don't feel good. You feel ill. And generally speaking, that's because many stereo-based displays present information where the focus of the display is at a very different place than the vergence position, that is the position in space where your eyes are converging to focus on that thing. So if you have that discrepancy called vergence accommodation conflict, that can make for a very uncomfortable experience. And our whole aim is to make this be an extremely comfortable experience to the point where you really eventually don't even notice that you have the device on. And so we've worked very hard to create a system that allows us to have this comfort across this breadth of this spatial computing range. And That's quite a large breadth. That goes from infinity in the far ground, basically, to mid-ground, which might be on the other side of your room, to near space, right up close where you might be reading or eating or doing activities with your hands. And so it was very important for us to develop a system that could do that. And so that's the optical system that the team came together with. It has a range. Basically, it generates 2 different focal zones in front of you. The focal zones are separated by about 0.65 diopters, so it's a very relatively small distance. There's never a vergence accommodation conflict greater than 0.75 diopters, which is quite comfortable. In fact, it's probably twice as comfortable as it needs to be, which is good. And it gets you a nice range of 37 centimeters to infinity. So 37 centimeters, just a little over a foot away from your nose, all the way to infinity with this range. We spent a lot of time determining that these were the right numbers by doing a lot of internal studies. And I think that's another thing that I really learned when I came to Magic Leap is there's so much that has to be learned about the human and what the human is able to perceive and what you might be able to get away with and what you aren't able to get away with. And so we have a whole group that's really focused on studying that, making sure we get it right. How do we generate the light field? Well, we have a spatial light modulator. It's a liquid crystal on silicon. It's a reflective spatial light modulator. So light comes in and is reflected off of that spatial light modulator and then propagates through a relay lens, which forms a pupil, kind of like a microscope out in space. And if you were to put your eye into that pupil and look back through, you'd see that image of that spatial light modulator occupying a 50-degree field of view in front of you, just like when you look through a microscope. But we want to put this on a transparent display of some kind. And so we use a light guide. And so what we do is we couple that pupil into that light guide using a prism or grating. The light totally internally reflects and propagates along the light guide. And then we have grating structures later on, further downstream in the light guide that couple the light out, and then your eye can look into that as if it were looking into the pupil and see the image focused at wherever you place it. And so this is a kind of a nice and powerful approach and allows us to have a nice wide pupil so that you can have variable head sizes. You can have variable head positions relative to the device. Everybody here who wears glasses knows that your glasses sometimes slip down your nose. We don't want the image to go away when that happens, so we have to have a nice wide pupil for that. So that's basically how the system works. Now, the nice thing about this system is that there's a light source, there's a relay, there's a spatial light modulator, there's a relay lens, and then the light source is actually imaged by this 2F system to the in-coupling grating over here and propagates. So we can use that to actually create multiple channels of visual information coming out of the same spatial light modulator that are temporally multiplexed. So if we have 2 different light sources and they're displaced slightly from one another and they go through the same spatial light modulator, now I can have two separate outcoupling pupils that get incoupled into 2 separate light guides that both are on top of each other, and then the light coming out of them is superimposed upon, the light coming out of each of them is superimposed upon the other, and it presents a single image. So if I've got a single pixel, and I do this, I can produce that single pixel image. So if I, on the back of the retina. So the nice thing about that is I can do full color and have 3 separate layers, 1 for each color. Or I can have separate layers, 1 for each depth, okay? So that's basically a really nice and flexible way to be able to switch depths in a system just using these optics and light sources can be switched very, very rapidly. So we built a system, and that's what's been integrated into the wearable that we have today, and the Magic Leap 1. And I'm proud to say that a lot of the key optics, these light guide layers, were developed right here in Austin, and the manufacturing techniques and the manufacturing systems were developed here too. So a little bit of local goodness. So in conclusion, I think spatial computing, it requires a lot of complex engineering challenges, but I'd say it's a lot of fun as well. It's been great fun for me going through this. There are many more opportunities for technology development and learning. Magic Leap works closely with universities, and we want to grow our relationship with UT as well, but other universities, of course, around the world, and there's a lot more to come, and so I welcome all of you to keep following us as we harmonize people and technology to create a better, more unified world, of course. Just a quick note, the best thing is for you to experience these things rather than just hearing me talk about them. And so we're going to try to pull together a little demo here at 5 o'clock during the reception. But I will tell you that we do have, and we are starting up regular demos at UT every month, first week of the month, first Thursday of the month from 3 to 5 p.m. at the PLAI lab, which is right over here near Bass Concert Hall. And so if you don't get to get a demo today, don't fret. Put your name on the list. We will contact you, and we will send details for that. Otherwise, hope to see you at the demo at 5 o'clock at the reception. Cheers.
Right. Thank you so much, Michael. This was a great presentation, learning so much more about the device that you guys have. So let's open up for questions. What a special gift that we get today here at 5 p.m. Get to experiment the device if you haven't tried it yet. So let's open up for questions first. Yes.
Hi. I was wondering, you showed some stuff about the Magicverse and this sort of outdoor experience of spatial computing. I know that some of these technologies don't work terribly well outside because of interference from the sun. How far off do you think we are from having experiences like that outdoors?
Yeah, it's a great question, and it's one of the other great challenges. Magic Leap 1 was not, I will tell you, it was not meant to be used outdoors. It was meant to be used in a sort of what we call outdoor adjacent, which I guess means brightly lit with outdoor light. I'm not sure what that means. But the point is that, the challenges that we have with the power that is required and the brightness that is required to compete with the sun is huge. So our next generation system will have some solutions for that, so quite soon. For now, I've seen people do creative things with our device, including putting, sunglass covers on the lenses when they need to go outside and do things. And I've done it myself and had a great experience. So it's possible, I will say that. It's just not elegant right yet. Yeah.
Cool.
One more question? I have one more for you.
Okay.
In one of your slides, you talk about this difference between, the traditional virtual reality experience, the traditional augmented reality experience, and then you have spatial computing. I'm just wondering about the authoring process of developing these new experiences. How much more complex is it to include the ability to design these new experiences with spatial computing?
That is a great question. Not being an author, it's hard for me to answer, but I do know that we have developed a number of tools to help with that. So, of course, as the system recognizes, say, for instance, a room like this, recognizes walls and surfaces, the SDK has features that allow positioning of things, kind of glued to those surfaces. So we can make portals in those surfaces. Of course, all of the physical and digital entities know about those surfaces and know the laws of physics surrounding them. So we've tried to make it as easy as possible with the SDK, and it continues to evolve over time. So that's about all I can say as far as that goes.
Okay,
Yeah.
sure.
Yeah.
Let's think. Microphone problems again.
wireless.
Yes. All right, so let's thank our speaker again. Thank you so much.
Thank you.
And before you leave, so a schedule check here. We're going to have our coffee break now for 30 minutes, like the one at 10. And we're going to have some posters again. So if you didn't have a chance to see the posters earlier today, so make sure that you check them now. This is your last chance to check the posters. And then after the poster, we're going to be doing two things. We're going to be having a series of presentations by ourselves, UT faculty who are involved in WNCG and who are going to be showing you some of the research that we're doing here that is connected to the theme of this year's event. So you'll be quite, I think, useful for you to see how you can also get involved. For some of you who are students, how you can get involved with this kind of research. And also for those of you in the affiliated companies, how you can get involved in this type of human-centered computing research here at UT. And then right after that, we're going to have our panel on this topic of virtual reality and augmented reality and so on. So, and then finally, of course, the reception at 5, where maybe you get to try out Magic Leap. So for now, let's take a quick break, and then we'll be back here in about 30 minutes. Thanks. Okay. Okay, welcome back, everybody. We are now in the final lap of our event. We have two more sessions. The first one is going to be the UT Research Showcase, and then after that, we're going to have the panel on virtual reality and mixed reality. So the UT Research Showcase, so the reason why we're doing this is because here at UT, here at WNCG, we're doing some great work, we think, in the space of human-machine sensing and interaction and computing in various different kinds of ways. And in fact, we are starting to work together and collaborate more and more towards creating a new sub-initiative within WNCG, the same way that we have SAVES, that's focused on autonomous vehicles, and MINDS, which is focused on machine learning. So we're working towards developing a new initiative in this space. And so we would like to highlight some of the research that we're doing so that you have a sense of what's going on here, so that you can get more involved in whatever way makes sense. We'll have more updates on this, hopefully soon. And so what we're going to do is we're going to have 4 presentations, and they're going to be fairly short. They're going to be about 10 minutes each. And maybe we'll have time for one question after each presentation. And then, and that's pretty much the time that we're going to have for this. So it's going to be about 30, more like 40 minutes. And so let's get started with the research showcase. So the first one to present is my co-organizer, Professor Nanshu Lu, who's been doing tremendous work here at UT, pioneering new kinds of sensors. So with that, let's welcome Nanshu.
All right. So when I looked at the program, I started wondering why I am the first, because as the co-organizer, we should be polite and speak after our other colleagues. But then I realized that, oh, they want me to warm the stage. So here I am being the first speaker. So in fact, Edison will be the last one. So I'm going to introduce to you very quickly about our wireless electronic tattoo technology. So I have been in UT for 8 years, and my group is focused on the soft bioelectronics in general. But in terms of fundamental research, we have to break it down to different disciplinary areas. The first is actually the mechanics of those thin films. We are using a lot of different materials like inorganic, organic, or even the hybrid of them. So how to make the structure reliable and robust, that is our first research thrust. And then after you have a good geometric design, you actually co-design the architecture with the circuits. We worry about how to manufacture them. So we are looking at the digital subtractive manufacturing process. And then we look into different materials, such as emerging nanomaterials, 2D materials like graphene. And we're trying to manufacture completely imperceptible tattoos. I'm going to show you some examples. But even if you have the perfect design, the perfect material, the perfect fabrication, if you do not care about the bioelectronics interface interaction, which can involve mechanical, thermal, optical, electrical interactions all coupled together, you are not going to get good signals or reliable readings. So we also worry about the bioelectronics interface. So our goal is to basically replace all the existing wearables by tattoo-like stickers. But those are smart electronic tattoos. Those are as thin, as soft as our skin, and they are able to have all kinds of deformation with our skin because of the mechanical contrast. So the reason current wearables are not able to do that is because of this intrinsic mismatch of their mechanical properties. So you can see the modulus vary by 6 orders, and the stretchability vary by tens of times. So moreover, our skin is microscopically rough. As Jean was talking in the morning, for elderly, they have even more delicate and wrinkled skin. So only when your sensor is able to fully conform to the skin and maximize your contact area, you are going to get good signal to noise ratio and limited motion artifact and very effective thermal or chemical exchange on the interface. So here we're comparing a dry but ultimate conformable electrode with a wet gel electrode, and you can see their interface impedance could be comparable. So how do we do that? We first engineer those kind of two-dimensional springs that can mimic the three-dimensional springs, such that you can make an intrinsically stretchable and soft circuit, even out of silicon metal. So this kind of 2D ribbons are in nano or micro scale, and they can be any material, silicon, metal, oxide, or even organic semiconductors. And we also look into digital fabrication process. Of course, the well-known one is additive or printed electronics. They have some limitations. So we're looking into subtractive manufacturing, where we can process already sheet-like materials like two-dimensional CVD materials and vacuum deposited gold, which is very expensive if you want to do gold printing. So we invented the cut and paste process, which is completely dry and free-form process, and you can do multiple iterations of this process, and you can integrate multiple materials and multiple devices onto one substrate. So this was our first cut and pasted e-tattoo on my arm. My first PhD student was twisting my arm, and you can see the tattoo-like behavior. And it first could be highly multifunctional. So here we are trying to measure the electrocardiogram, skin temperature, and skin hydration simultaneously while the subject was subjected to some hot wind. And you can see while the hydration increased and saturated, that represents a lot of sweat on the interface. And we are still able to get very accurate temperature and ECG readings. And it can also be multi-material. So here we integrate gold as the electrocardiogram electrodes and piezoelectric PVDF polymers as the vibration sensor. So instead of using a stethoscope, now you can use an e-tattoo to measure the mechanical signal from the heart, which is called the seismocardiogram, SCG. And if you have synchronously measured ECG, SCG, you can figure out all those cardiac time intervals. And one of the interval, which is the RAC interval, is negatively correlated with our blood pressure. So that gives us a way to continuously and beat by beat estimate our blood pressure using a single integrated non-invasive electronic tattoo. And that is highlighted as the cover on Advanced Science. Moreover, this cut and paste process can be large area. So we demonstrate that you can integrate a 16-channel electromyogram e-tattoo which completely covers your forearm because all the muscles on your forearm contribute to your sign language. So using this kind of e-tattoo, we are able to interpret all 26 letters of the sign language. And because this is so thin and so soft, it doesn't require any sheaths or cover. And compared with the more thicker and non-breathable devices, our device has much lower temperature and much more breathable. So ultimately, we are able to make completely imperceptible e-tattoo using graphenes. Graphene are single layers of carbon atoms that are still electrically conductive and thermally conductive. So we can make them directly on a tattoo paper, and we can directly paste them like a tattoo sticker. So this is how you transfer directly like a temporary tattoo. And under microscope, you can see how conformable and how thin it is. And while you wear such tattoo all the way on your face, no one can see it. Right? And then we can actually use your eyeball rotation, which induces surface potential, which is called electrooculogram, to control a drone. So there's no camera on the drone, but we are able to ask the drone to follow the eyeball rotation of the subject. And there's no way you can see it, so we call it imperceptible tattoo. And ultimately, to go wireless, we upgraded our cut and paste method to cut solder paste method, where we can integrate all the off-the-shelf ICs onto our stretchy e-tattoo. And we can stack them up in a modular design where you have your sensor layer, readout circuit layer, Bluetooth transmission layer, and NFC charging layer, such that when you stack them and patch them onto the chest, we can directly measure single-channel ECG, seismocardiogram, and 3-axis of motion. And the Bluetooth, of course, is power hungry, and we cannot afford adding too big of a battery, so we have the NFC charging layer that can do real-time charging on the go. But ultimately, we don't. This is actually a demonstration of how robust and rigid the system is. It's even bendable, stretchable, and waterproof. But ultimately, we don't want to create more disposable electronic waste. So eventually, we are able to even disassemble those different layers after our measurement, and then just dispose the bottom layer, which was in direct contact with our skin, and then recycle those readout circuit, Bluetooth, or charging layer. So in summary, e-tattoos are hair-thin, skin-soft wearables that has no limitation in terms of location on your body. And you can use them to sense all kinds of electrical, mechanical, thermal, optical, or even chemical biomarkers, as Professor Wei Gao mentioned very well in the morning. But there are some challenges. We are still trying to figure out ways to hybrid the rigid component and the soft, stretchy interconnects. And the power and the data are always big limitations, and the long-term wearability is a challenge. With that, let me acknowledge my group at UT and our sponsors. And because we're from Texas, so in addition to research training, we also offer shooting training. Thank you.
Okay, great. Any questions? No question? Gotta have at least one question.
It's okay.
No? Yeah. Okay, so let's keep moving then. So next we have Professor Jose del Milan, who recently joined us from EPFL. We're very excited to have him here. He's doing tremendous work in the space of brain-machine interfaces.
So thank you very much. Here at the UT Austin, I am still building up the laboratory, but let me show you what we have been doing over the years and what we will be also replicating and extending here at UT Austin. So multitasking is not my best. Let me concentrate on this. Yeah. Okay, very good. Here it is, very good, thank you. Very good. So this is the kind of research that we have put the focus on over the last years, how people can use a brain-computer interface in order to modulate their brain signals and control different robotics devices. So we have been doing that in the framework of, first of all, testing with healthy volunteers and then transferring that to people with different kind of motor disabilities. So this is essentially in the framework of assistive devices, so as to compensate or to allow people with motor disabilities to do what they cannot do through these robots. In addition to these, okay, this is not working. Oh, this is frozen. Sorry for that. This is frozen. Let me redo that. Okay. Here it is. In addition to controlling physical devices, like in the slides before, we have been also working with people with disabilities in order to offer them other kinds of visual control and interaction. This is the case of an avatar competition, the so-called Cybertron, where people with disabilities were controlling their avatar that you can see in the upper right part. In order for the avatar to win the race, they had to deliver different mental commands according to the color of the path this avatar was in. And through this longitudinal study, because we had to train these people over a period of time, months actually, we were capable to track their learning process, not only in terms of how they were acquiring BCI control, but also the changes that this acquisition of BCI control engender into their brain rhythms and brain patterns of activity. That calls then for the fact that if we are capable to induce plastic changes in people's brain through the operation of these BCI systems, then we could extend the use of BCIs beyond the realm of assistive devices to reach neurorehabilitation. How a BCI can accelerate, can enhance the recovery of lost motor functions, for example, after a stroke. So in that case, what we need to do is not only to use the BCI to decode the intended action that the patient cannot do, but also to provide a feedback that is naturally coupled to the motor function that we want to recover, in this case, through the electrical stimulation of the peripheral nerves that will contract the target muscles and produce the movement that they cannot do. And this actually is the basis for these people to recover function, as you can see over here. And this function is sufficiently recovered so that they can achieve tasks, do tasks that they couldn't do before. But what for people without disabilities? So there we have been exploring a few things. One of them is in direct translation of what a BCI is. How can we control different devices? For example, these sophisticated machines that are replicas of the original machines and mechanisms of the Industrial Revolution in an art science exhibit that was deployed in Lausanne, in San Francisco for a number of months. Almost 800 people had the opportunity to work with those devices. We are still analyzing that huge amount of data, so one day you will learn what we learned. But essentially what we observe is that these people indeed, through this immersive interaction, they acquire control very rapidly, and that there are also changes in the patterns of brain activity that they are producing in order to acquire that control. So a kind of replication in a very open, wild space and with a very short time window. But beyond the pure BCI control, we have been also exploring how a BCI can augment the interactive experiences that we all may have with intelligent agents. And one prototypical example of an intelligent device is a smart car, a car that can do many things for us. But the important thing is that this car does what the user wants or is expecting the car to do. So the key question here is not to drive the car by delivering mental commands. We are not that crazy, at least not yet. What we want is that while the person is driving, infer which is the action, which is the cognitive state that this driver is in, so that the action that the car will undertake will support the intention of this subject. So, for example, predicting ahead of the actual movement when the person wants to change lane. And at that moment, the car can assist in this lane change, or can inform the user that, nope, this is not a good decision, because maybe you didn't see this car approaching that was in your dead angle. Another realm of exploration is in sports. How can we derive critical information that we could use as people are getting trained to perform in sports? So in this particular case, with colleagues in France, we developed this, well, actually they developed this sophisticated virtual reality environment where people can get trained to shoot. And we were training these people in immersive environments where they were in two situations, where one was training, they were alone, shooting, and then they passed to a competitive environment where they had to compete with other avatars that were representing other athletes and with an unsupportive crowd that were shooting and booing to our avatar. And at that moment, what we expected to see were changes in brain activity that were indicative of when they were performing good or bad. So we didn't get direct evidence of that. However, we observed that there was a clear correlate that was indicative of when, as compared to the training performance, the athletes were about to shoot a good shot or not. And we could then, we can speculate that this could be the basis to develop personalized trainers that will inform on the fly to the person before they are shooting when it is the good moment to shoot, in order to allow them to modulate their brain signals in order to be, again, aligned with their physical performance. Finally, we not only try to decode motor-related movements, motor-related patterns of brain activity, but also other kinds of cognitive patterns that are associated to the fact that whenever we are interacting, we need to process the feedback that we are receiving as a consequence of our actions. So imagine now that you are trying to control with a BCI this wheelchair, and you want to deliver the command A, but actually your BCI takes wrong your intention and start moving the wheelchair in another direction. So at that moment, what will happen is that immediately you will realize that there is a mistake because you wanted the wheelchair moving in one direction and you feel that the wheelchair is moving in another direction. And in your brain, this signal that appears milliseconds after, you realize that this is not the good movement of the wheelchair. Now we can decode that signal in order, for example, to develop this kind of spellers where the cursor is moving randomly at the very beginning in the screen. As far as the cursor moves towards the target letter that you have in your head, nothing will happen. As soon as the cursor deviates, you will generate this error-related potential. And now you can drive the cursor towards those areas where most probably is the letter. And actually, people can write words with shorter and shorter times as this speller learns, which is the intention that you have in your head. This is not only with healthy people, but also with ALS, people who have a neurodegenerative disease that gets them paralyzed completely. And finally, something else that we are exploring massively is how we can use these error-related potentials in order to teach robots, so that we can not only teach the robots how to execute simply by observing what the robot is doing, and our brain will be eliciting these error-related potentials whenever the robot does something that it is not what we want the robot to do. So we are not only teaching the robot to do so, but the robot is also acquiring personalized trajectories, because everybody will have a different set of parameters so as to generate whatever behavior the robot has to do. So I stop over here, and I will be pleased to take any question that you may have.
All right. Thank you. Thank you. Let's see. Any questions? No questions? Okay, we have one question. Excellent.
So in the BCI, the focus is mostly for the ALS patients, like the who are disabled in some way and who are able. Like, what can it add to the abled persons? Like, as one of the example you have shown for shooting, practice shooting to kind of get the feedback. So how much it is helping, and what other use cases it might help?
So, as I have said, I have illustrated several of them. Training people can be one possibility because, of course, you can train and train and train behaviorally until you acquire your skill. But it seems more interesting, and definitely this is the case for high-level athletics, that physical improvement is reaching the limit. So now it is how we can train the psychology of these athletes and how we can train the neural correlates. Because if it is true that behavior is an expression of our brain activity, one way to improve behavior is to improve the brain patterns that are associated to that behavior.
Just another thing. So in all of your like experimental setup, it was mostly the ECG measuring device on the head, correct? And with a weird kind of setup. So in Neuralink, like they are kind of proposing having some implantable stuff to get like magnify the signals. Obviously, there are issues because you have to implant, but how much, if that is possible, like how much improvement we can get in terms of signal and other kind of information?
Well, all the examples that I have chosen today are based on EEG. This is the core of our research. We also do research with implanted devices. But as you say, there is a price. There is the implantation. So there is a medical risk and there is a price. So this is only acceptable for people with high degrees of disability, not for you and for me. I have never found any healthy subject who volunteers to have an implant for my research. But if you want, we will be happy.
Okay, I have a questions about the because when people want to do something and plan to do something, there's some kind of difference. Because maybe I plan to turn around, but I didn't turn around right now. So whether your system can distinguish these two differences?
So the interesting thing is that when you analyze brain activity while you are planning to do so and you actually block the execution, this is called covert behavior because you are not actually executing that behavior. You are only, rehearsing that behavior in your head. The kind of patterns that we observe over the motor areas of our brain are the same, or at least very similar, to when you actually execute. And this is the basis of a brain-machine interface, that you are recruiting the same areas, with subtle changes, of course, but they are the same. And this is what we are using in order to, for example, in the case of the drivers, to predict ahead of their execution that they are preparing to do something.
Okay, thank you.
This gives the car the time to assist them.
Okay.
Thank you very much.
Any other questions? Any volunteers? No. Okay. Thank you. Now we have Professor Lily Chu from Computer Science. Professor Chu is also a member of WNCG.
Hello, everyone. It's my great pleasure to have the opportunity to share some of our recent research work on motion tracking and applications. Imagine that you can simply wave your hand to change a TV channel, or when you are cooking, you can just do a simple gesture to pick up the phone. This is just some of many examples that motion tracking and gesture recognition can enable you. Other examples include gaming, interact with smart speaker, controlling VR, AR, or even controlling the drones. To better appreciate why do we need motion tracking and gesture recognition, let's watch a quick video clip. Somehow, let me try to see if I can play in the edit mode. As you can see, without a good motion tracking, it would be painful to play any VR, AR, or even regular game. So what we need is millimeter level accuracy in order to enable this type of applications. And the first thing that comes to mind is using computer vision. Computer vision is great, but it has its own limitation. First of all, it may raise privacy issues, and also cameras, existing camera has a limited range and field of view. More importantly, the minute you turn on the camera, the battery drain. In fact, we tried on iPhone leaving the camera on without any video analytics, just leaving it on for 1 hour, battery dropped by 30%. So what we do, another option is using RF radio frequency. For example, Wi-Fi has been widely used for localization purpose, but the accuracy is pretty low. The best we can get still is on the decimeter level. 60 gigahertz has potential, but it's not widely available yet. So what we use is acoustic signals. Why? Because speakers and microphones are cheap and it's everywhere. It's on your phone, it's on your smartwatch, on your TV, on your laptop. We use easily transceived speaker and microphone to transmit inaudible sound, and we can enable high accuracy because sound propagate much slower than RF frequency. Moreover, sound has a low sampling rate, so it enables us to do fast software processing and achieving energy efficiency. We have developed both tracking technology for tracking a mobile device and also tracking a free moving hand, as well as several applications on top of it. So our approach is to explore existing infrastructure such as speakers and microphone you bought for $10 from Amazon, and then we developed a simple app what's not trivial is can we achieve high accuracy, and can we even enable device-free tracking, track a hand without wearing any devices. And we have developed several approaches. Here, in the interest of time, I just describe one of this approach. In this case, we track a device by using Doppler shift. So we know that due to movement, the frequency change, and the amount of change is exactly correlated to the velocity. By analyzing the frequency of the received signal, we are able to estimate the velocity. Based on the velocity, we are able to derive distance and able to run triangulation. Here we show the distance estimated by Doppler shift versus ground truth. As you can see, they closely match each other. And we also developed other technique to directly estimate the. I'm trying to show the video again. To directly estimate the distance, there the main challenge is that because the speaker and microphone are not synchronized, so how can we estimate the absolute distance without strict synchronization? And we developed a technique that eliminate the need for synchronization. And here are some applications we developed. Some of these are games, some of these are VR, and also we can control the TVs by simply moving your phone, running our app. And it is cheap enough that it can run on the smartwatch because we can explore the microphone on the smartwatch to pick up the sound. And we further applied it to enable some other application. For example, follow medium. In this case, we have a smartphone app that processes the signal arriving at microphone, and then using that, we are able to locate where the drone is. Then we run our control algorithm to decide where drone needs to move in order to strictly follow the user. There are lots of interesting challenges in this case because when the user is moving in the indoor environment, there are lots of furniture, walls, so this creates a rich multipath interference. We develop a technique to get a high resolution distance measurement, and also we are able to filter out the noise generated by the drone itself so that we can focus on the signal for tracking purpose. And based on the tracked information, we are able to directly derive what the drone needs to do in order to follow the user. To do that, we use the model predictive control to compute the command for the drones. And here is a video demo. My student is working in the computer science building, and we mount a mini speaker on the drone to emit inaudible sound for tracking. And the student is holding a smartphone running our app. The app real-time compute the drone's location as well as the command and sends through Wi-Fi. As you can see that it not only work in the line of sight, but also without line of sight because acoustic signal can penetrate certain objects. And that is great. We can enable tracking for a device, but is it possible to directly track a hands without wearing device? Why do we need that? Because people may find it's inconvenient to always hold on to a device, and sometimes it's very hard to remember wearing the device. So we want to just move our hand to control things around us like TV or VR or AR. Such capability is available in RF radar, but the problem with the existing radar system is it's bulky and expensive. It requires ultra-wideband and also special hardware. Is it possible to enable finger-level tracking for the mobile devices that use very limited frequency? And to do that, we found that acoustic is possible because we could use phase-based tracking because acoustic wavelength is small enough, so even 1 millimeter change converts to 0.21 pi phase change, which is noticeable, and we can measure that. But the problem with that is there are lots of reflection around us, not only from the hand, but also from the furniture, the walls. So we developed a technique to decompose signal with different delays and extract a signal that corresponding to the target we are interested in tracking. And this is a simple game we developed, basically showcase that we can enable freehand tracking. In this case, our app basically emits the inaudible sound, and then the microphone will pick up the sound, and we are able to use the reflection to track the hand's movement in real time. But can we use the reflected signal to enable room scale level device-free tracking? This is challenging because refracted signal is very weak, and its room scale make it even weaker. So is that even possible? But before that, why do we need that? It turns out for smart speaker, it's an ideal application. A quarter of US household has smart speaker, and almost half of them own multiple smart speakers. Current smart speaker use voice-based command, but this does not work in quiet environment or noisy environment or complicated operations. For example, if some of the smart speaker come with display, if you want to choose certain menu option, it is very cumbersome to use voice-based command. So we envision that in the future, smart speaker could also accept gesture-based interactions. And we developed interesting tracking algorithms and systems to enable that. And here is another demo I want to show. Basically, here we developed a simple prototype that uses mini microphone array, and then we are able to use the reflected signal to process the incoming signal and direct real-time track the user's hands movement. The user is around 3 meters away, so we are still able to use such a weak signal to accurately track the hands movement. So far, mainly focused on tracking. Is there other application we can leverage? And we recently tried using acoustic to do acoustic imaging. Why do we need that? Because acoustic signal penetrates certain objects, so it might be useful to do weapon detection if there's a metal underneath your clothes and acoustic signal penetrate. But we are not looking at expensive hardware to do that. We are just looking at a smartphone, simply swipe across the object, trying to detect what's underneath. And my student and I developed a system basically that shows that this is possible by simply using a smartphone. So as you can see, we developed an app running on the Samsung S7, and we use movement to create an antenna array and then able to image the object. And we can even image the object that is under the plastic bag. So what's next? Since 6G or 5G beyond, it's a very exciting topic. We are very interested in trying motion tracking to help wireless communication. Why do we need that? Because wireless channel, especially under high mobility, it's very hard to predict due to multipath and also complicated environmental change. So if we can predict the motion and using the motion, we can potentially improve the channel prediction accuracy and enable predictive wireless optimization and also realize wide area mobility management. So with that, I'm very grateful to my students, and I'd be happy to take some questions. Thank you.
Any questions?
Yeah, I think the refracted signal will become much weaker, so you will reduce the accuracy. So basically, what we are trying to do here is we use a single, and in order to do imaging like ultrasound at a hospital, typically you need this antenna array, but smartphone only has one antenna. So we basically use movement to create, to simulate this antenna array. So in order to do that, we need to know roughly the position of these antennas. So we need to have a predefined trajectory, but the hands are allowed to deviate because the hands are not going to be that precise. So main complexity is how to deal with this noise coming from this deviation. Thank you.
Okay, one question.
So let me get rid of all this. So I was saying fantastic. I wonder how complex is, or if it is at all necessary to do any kind of calibration before you can use your approach?
For that, we don't need to do much calibration. The only thing we need is we need to know the speaker's distortion. For that, we just let the speaker transmit the sound at our band so that we know the frequency profile.
Okay.
Okay, in the interest of time, let's wrap it up with Professor Chu. Thank you so much again. Okay, and so I'm going to be the last presenter. So I'm going to be relatively brief because we still have our panel. So just 1 second. Okay. So what I'd like to do is just give you an overview of some of the work that we're doing in our group. And so the title is Advancing Digital Phenotyping, New Directions in Wearables and Beyond. So what I'd like to do is I'd like to start by talking a little bit about what I mean by digital phenotype. So digital phenotype is a concept that digital technology is embedded in our lives so deeply that it's possible to characterize health and disease based on how we interact with our personal devices, particularly smartphones. And as it turns out, this has actually been demonstrated in several studies that have shown, for example, that depending on your patterns of interaction in terms of phone calls and text messages can be indicative of whether you might be depressed if you haven't placed your regular phone calls to friends and family, for example, for certain amounts of time. That might be an indication that you might be depressed or maybe you're sick. So this has actually been demonstrated before. And we are particularly interested in thinking about this idea of the digital phenotype, but in a more sort of broad sense. And so what if instead of just thinking about our interactions with one device, we think about it in the sense of monitoring the whole spectrum of our everyday activities and then linking those everyday activities to states of health and disease, and then build these predictive models that can be early warning signs of what could be going wrong with you, or perhaps provide you with guidelines for how to continue doing the kinds of things that you are doing that are working out. And so this is one of the general thrusts of interest in our research group, and I wanted to tell you a little bit more about some of the things that we've done in this space. So in general, we touch on a variety of different areas of research methodology, I should say. So we develop novel sensing methods, some computational algorithms for processing the data from these sensors. We also develop some tools and infrastructure that supports this work. We run human subject studies, and at the end of the day, we end up with data sets that sometimes we also share with the community, and those are usually contributions in our field. So I'll briefly talk about two of these areas. One is novel sensing, and the other is on the computational algorithms. So for quite some time now, we've been interested in this problem of dietary monitoring. It's an area of research that I've been working on for at least 10 years or so. And as it turns out, eating detection is really, really important to identify certain kinds of eating disorders, for example, and there are many other applications for it. But as it turns out, if we take the traditional view of the digital phenotype, it's not really possible for us to track dietary activities using, for example, just your mobile phone, right? It's extremely hard. So we need to think outside the box about how we're going to be doing this. And so we've been thinking about how we can develop novel devices and novel sensing approaches to solve this problem. And one of the ways we've attacked this problem was by developing a wearable necklace about 2 or 3 years ago. And we wanted to be able to see if we could track, for example, jawbone movements with this wearable necklace. And we were pretty successful at this. I can show you here some of the signals that we got from this device. And this device is basically just looking at, just go back here so that you can see. It's basically just looking at the distance between the device itself as it sits on your sort of base of your neck up to your jawbone. We're just looking, it's a very simple measure, which is actually good in this case. And it's just looking at that distance. And so it's just using a light-based proximity sensor looking at just time of flight. And we were able to see that the signals that are indicative of different activities are quite unique. In fact, in particular, the eating signal here is quite deterministic in terms of us being able to identify that eating is taking place. So this was good. As we usually do, we ran some studies in the lab, and we ran some studies in the field, and we got some pretty good results. Obviously, it's a little bit easier to get better results when you're in a lab, but we also got some pretty good results in the field. We were quite encouraged by that. But there were a few issues with this approach, one of which was this device was very sensitive to its exact positioning. So as with any type of necklace type device, it moves around as you're moving around, and so it was a bit hard sometimes for us to keep it in the location that would allow us to track the jawbone accurately. And honestly, I mean, this was technically an interesting and promising approach based on our results, but the likelihood that someone would actually be wearing this on a daily basis is actually quite low. So we started thinking about the next generation of this device or this type of approach. And this is what we came up with. We took inspiration from the Band-Aid, which can be quite small, and you can essentially attach it to pretty much anything. And so we developed a new architecture. And the nice feature of this is that we can actually eliminate this sort of mechanical problem of having the wearers move around. So we can basically stick it to the jawbone itself and make it such that it's not visible and also can track more accurately what the jawbone is moving. So we are about to submit this work, and we're quite excited about it. But we think that there are many, many more possibilities in this space, and so we're moving forward. And so I'm just going to give you an idea of the next directions of our research in this space, which is going actually inside the body, so actually doing some computation inside the mouth. And so we've developed an even smaller device, and we've actually run some experiments now where we can actually have this device running inside the mouth with a battery and so on, which is biocompatible. And so some of the applications that we envision here are, again, dietary monitoring, being able to identify actually food categories and actually the amount of food that you're eating, and just oral health in general, and potentially even physiological sensing that you can do by being in direct contact with saliva, for example. So this is on the side of sensing. And very quickly, I just want to talk about also some of the computational methods, because our research really cuts across all these different areas, from sensing all the way up to human subject studies. And one of the problems in the space of activity recognition is, how can you collect lots of data from real world sort of situations, and then you annotate it. Now, it's actually quite expensive and difficult to do, quite time consuming, and so we explored how we can use, for example, active learning to reduce the burden of annotation. And active learning is sort of this idea that you can take a pool of unlabeled data and you apply this algorithm that's able to identify what are the most promising, the most informative labels that should be annotated. And so when we tried some of these algorithms, we got some really good results on some existing data sets. For example, the opportunity data set and the PEMAP2 data set, we were able to show that we could get fully supervised performance by essentially annotating only a percentage, very small percentage, 10%, 8% of the data set, which was really great, right? So you essentially reducing the amount of annotation you have to do by almost 90%, and you get the same kinds of results. But if you have some new data set and you don't know anything about it, you start applying this algorithm and it starts giving you instances that you should annotate. The question is, when do you stop, right? Because it's just going to keep doing that. There's no stopping to it. It's basically just identifying the most informative label, or the most informative instance for you to label. So when do you decide when to stop? And so we came up with an idea for how to do this. What if we stop this process when the amount of information gained converges to very small values, close to zero? And then we came up with a measure based on what we ended up calling conditional mutual information. And again, just going through this fairly quickly here in the interest of time, the idea is that this conditional mutual information measure sort of approaches zero as more training data is added, and eventually there is no more information gain from this process. And so we came up with this stopping criterion where, based on a fixed threshold and also the number of iterations, we can tell when it's basically not going to be worthwhile to be continuing with this annotation process. So I am going to stop now, and I'd like to again thank my students, who actually are the ones who are doing all this work. I'm just helping them, guiding them, but they're really the one doing the hard work. So these are some of the areas of research that we also do in addition to what I've talked about. So thank you so much, and I'm happy to take any questions. Yes?
So how did you fix the device on the inside of the mount?
There's been several iterations on that, and one of the problems is that batteries are still a problem, because the device, we can actually make it quite small, but the battery it's a little bit harder. So we've tried different approaches where we have the custom board that we built together with the battery together, and then it was a little bit too kind of clumpy to have both of those in one place, so then we kept them separately. But we use dental floss for a lot of it, and we actually 3D printed a small little surface that allows us to keep it more evenly against the gums and all that. But we're still working on that. That's actually an interesting problem that we're dealing with. So, yeah. I don't remember the exact specifications of that, but we started looking at batteries in hearing aids as one direction, because those tend to be quite small. But in this case, one of the problems is that the battery has to be biocompatible, because if you do happen to swallow it, you don't want it to be toxic. You don't want to get sick because of that, right? But future, we're also looking at power harvesting in different ways, either using the domestication itself or some other means. So inductive charging, I don't know, something like that. But again, we're very close to the body, we're inside the body, so we're somewhat limited, but those are some of the interesting challenges of this type of research.
So how do you select the sensing modality for a particular problem? Like that kind of ties up to the energy and the accuracy. For example, you were looking at the distance, correct? So you could look at the audio, you can look at other sensing modality. I'm not sure what kind of sensing you are doing inside the mouth. Yeah.
I'll answer that very quickly because we have to get going with the panel. But I would just say that I think, again, back to power, that's a critical component, right? So we need to be very efficient in how we're doing things when we are restricted by power. And so this is what made sense. And by the way, we still have communication that needs to happen here, right? We need to be able to communicate with a phone, for example, to send information back and forth. So, happy to talk to you later on about this. So for now, let's just wrap this session up and move on to the panel. So thank you again. It was fine with Nancy. She had just this one, and I think they had two. Yeah. And so. Okay, so let's start with our final session, our final panel of the day. And this is going to be around virtual reality and augmented reality, mixed reality. So we have three amazing panelists for this last session. And I'll start here in the order. So we have Adam Kelly, who is, well, I'll let you introduce yourselves once you come down. We also have, yes, yeah. Why don't you come? Why don't you come and we'll start the panel. We'll start the panel from there. So we'll make it more informal since this is the last session of the day. So.
Need to borrow.
All right. So thanks again for being on the panel here, and very excited to talk about this topic. We've covered some ground earlier today, some exciting presentations, and so why don't we have a minute or two of just introductions? You can talk a little bit about who you are and the work that you do.
I'm Todd Humphreys, an associate professor in the aerospace engineering program here at UT. Why am I talking about virtual reality? Do we use that in aerospace engineering? Well, it turns out that there are good reasons to do virtual reality, augmented reality, supported by drones that can be programmed to map an environment, recreate that environment, and then render it to users. I also, together with my students, I'm interested in absolute location for virtual reality that enables placement of persistent objects so that you can return to them decades from now, even if the landscape has entirely changed, and still find a virtual object that you placed there. That requires precise, say, centimeter accurate positioning, and that's something we do in the aerospace engineering department. So my greatest interest is in outdoor uses of virtual reality. And I know that's controversial, but I hope to persuade you that there's some good reasons to go outdoors.
Hi, everyone. I'm Kiran from Facebook Reality Labs, and I'm an applied science manager. Our lab is an integrated lab where we do both hardware and software integration for AR and VR research. My particular research area is in SLAM and semantic understanding of the environment. And we're not outdoors yet, but you want to get there.
Hi. Well, that's louder, huh? My name is Adam Kelly. I am a software engineer at General Motors here in Austin, Texas. I work on a small research and development team, and we do some projects with artificial intelligence and some with robotics, and I've done some projects with virtual reality. But before working here at General Motors, I actually worked at Microsoft on the HoloLens team in Seattle for about 3 years. And so I kind of go back quite a ways with virtual reality. And during that time, I also started a virtual reality blog, which has morphed into an artificial intelligence blog and YouTube channel. So that's kind of my story.
Excellent, excellent. So, before we get started in terms of, asking and talking about, asking the tough questions and talking about some of the really thorny issues and all that, I just wanted to offer sort of a historical perspective, and I have some slides up here. So, here's the Oculus, right? So it was founded, the company was founded in 2012, and then it was acquired by Facebook in 2014. And then the Magic Leap, the company was founded in 2010, and it was, it revealed its headset in 2018. Here's the HoloLens, which shipped in 2016. And again, in terms of perspective, so the Google Glass, right, which was another headset that was became quite popular. So that became available in 2013. And was discontinued in 2015. Right? And so it just gives you a sense of sort of where we are in terms of how many years have gone by since we've had this latest sort of generation of virtual reality and excitement in this space. And lately there's been some interesting developments that we can talk about. So there's a lot of evidence that, for example, Microsoft is putting a lot of resources on HoloLens. HoloLens 2 just came out with some interesting features. It looks like it's going to be focused primarily on I shouldn't say primarily, but there's an emphasis on enterprise applications with HoloLens, and we're hearing more and more rumors that Apple and Samsung and others are going to be announcing consumer-targeted headsets coming up. So this is sort of where we are, right? And the reason why I think this is valuable is because the space has been sort of on and off for a long time, and so it's useful to sort of think where we are. But I think we're getting some significant traction now. Lots of different technologies coming together to make this work. So we're going to be talking about many of the things that we that came up here in the introductions. And again, I think one of the topics that's really interesting for this event is the extent to which virtual reality, mixed reality can drive demand for new kinds of communication services and resources. So why don't we start with you, Todd, on this topic of augmented reality or outdoors VR, or the way you perceive it. So what exactly is this? Why are you so excited about this area?
Well, first of all, I should note that my favorite way of describing all of this is now XR. So it's extended reality.
XR,
that's the umbrella term that encompasses everything. I find it hard to distinguish sometimes between AR and VR when you're talking about videos passed through. I do think it's really relevant here at the Texas Wireless Summit. When we talk about 5G, Qualcomm this morning talking about 5G, and John Smee this afternoon, XR was front and center there because it's one of those few applications that can drive the latency that the 5G is wanting to offer. And John made the comment that Qualcomm is working on XR in a kind of unbounded sense, an unbounded XR, and that's really my interest too. I want to be able to engage in a virtual experience outdoors when I'm exercising, when I'm walking around a park, when I'm even when I'm driving. And I know that sounds ludicrous because of all the safety problems and the social stigma. So I'd almost want to cabin the safety issues and the social stigma and say, you know, we'll deal with them somehow. And if we don't, you know, it'll fail. But imagine we could cabin the social stigma. Imagine we could cabin the safety problems, and we could be in a virtual environment for a much larger portion of the day than anybody's experimenting with at present. What kind of enhancement of our living experience could be achieved, or what kind of dystopia would that lead to? I do believe that it's pretty much inevitable. Microsoft just last week or 2 weeks ago published a paper called Dreamwalker, where they imagine a kind of pure virtual reality experience while a person is working from one building, walking from one building to the next in the campus.
I think I actually have a video here, but if we have a little bit of time, we can play the video later on, but it's quite remarkable.
I was really gratified to see this because my students and I have been poking around with outdoor applications of virtual reality and have been listening to people giving us plenty of flack for this. And now I have all of Microsoft to point to and say, well, it wasn't that bad of an idea because Microsoft is behind it. And I think what was going on here, and maybe Adam can chime in, I believe that Microsoft sees themselves as having missed the smartphone revolution, maybe with regard to the software, maybe with regard to the hardware, and they're not going to miss the next revolution in their mind. So their HoloLens, I think HoloLens 2 is the state of the art, and these dalliances with outdoor virtual reality, with Dreamwalker, point to their being very serious about this space. Is that right, Adam?
Yeah, I can agree with that. Definitely on the mobile front, they definitely lost that. And they've said that publicly recently. I think Bill Gates was just talking about that. But yeah, so I was on this team when it was still secret, but even during that time, they were very serious about it. They had some of the best engineers at the company working on HoloLens, and then the VR stuff sort of came along after the HoloLens team was fully established. But yeah, they definitely seem to be very serious about it. I don't know how serious everyone is about walking around campus wearing the headset, but...
Yeah, and so this experience here is quite interesting. So the scenario here is one where you go from A to B physically, you walk from one side of, say, campus to another side of campus, and the whole time, right, you have your headset on, but as you are walking, what you see within this virtual environment is something obviously completely different from what you are experiencing in the physical world. So you could be walking from one side of campus to another, but you are actually within a forest, right? You were walking down a path on a forest.
It doesn't have to be that way.
It doesn't have to be that way, right?
And the outdoor virtual reality experience that we are trying to enable in my lab is one that is built around the environment in which you're walking. So we send out our drones and we map the environment with exquisite precision and absolute location. And then we render that same environment perhaps augmented or enhanced artistically according to your own tastes. Maybe the sky is bluer, the grass is greener, and there are birds and leprechauns and unicorns. So you still adhere to the structure so that you can reach out and touch something so that you don't run into the fixed objects. But you overlay a skin on the world that allows you to experience it in a whole new way. So you can either do it the way they were doing it and generating it in real time, or you can do the mapping beforehand and have an even cleaner, crisper looking experience.
That's great. Yeah, I definitely wasn't attuned to this possibility, of course, because the example that they gave was one where you were somewhere else completely. But absolutely, you could do exactly that.
Right. So they had somebody walking across the campus in Redmond, and yet they were representing them as being in the middle of Manhattan.
That's right.
And I think that's just the opposite of what you want to do.
Yes, that's right. That's exactly
right. Manhattan and put them in the.
And by the way, you might be wondering, how is it possible that you can do this and not, bump into people and other things? Is because, they have forward cameras that are looking at your environment and it's guiding you so that you don't bump into anything or do anything that could be bad for you, harm you in any way. But I would like to bring Giri into the discussion. What are your perspectives from Facebook's Reality Labs on this perspective of XR, right, in the context of sort of being in the real world?
So the way we represent it is like there's a trade-off axis between ubiquity and immersivity.
Mm-hmm.
So these kind of experiences give you ubiquitous XR, right? So you're able to experience XR everywhere. But for that to become a reality, we probably want to shrink form factor. You don't expect people carrying around backpacks and actual VR headsets. So we actually believe in glass form factor there. And I think that's the form factor which is going to allow for ubiquity. Whereas VR, it's mostly restricted to room scale experiences, maybe building scale experiences, where like pre-mapping an environment becomes feasible. And there are a lot more experiences we can enable that way. So I think the list of products and experiences is around the trade-off curve of ubiquity and immersivity. I think we don't have this singularity where we're able to achieve both right now, just because of silicon limitations.
Right. Now,
the only advantage I see, though, of an AR experience, and the way I distinguish AR and VR is that photons from the sun, say, or from the room lights can reach your eyeballs in an AR experience, where in VR, maybe those photons never reach your eyeballs. But I really don't see any long-term advantage to AR, except that other people can see your eyes. And maybe if we could have some representation on the outside, because you can always do a video pass-through in even a very faithful representation of the environment, and maybe even more faithful than your own eyes can represent. You can enhance the visual scene in ways that your own beyond what your own eyes are capable of. So what is the long-term benefit of AR, except to give people a sense that they have a better situational awareness?
So 2 comments on that. People do think that eye tracking, like for social interaction, is very important. So unless you have like see-through, like usually see-through is like you're able to see the environment, but reverse see-through, right? We're able to see the eyes.
Right.
That could be a possibility. But to me, like AR or VR, it's more about the form factor. We could have like block light AR through a VR display, but as long as it's like all day wearable, I think that's where the distinction would be. So it's more on not whether it's block light or pass-through, it's more on form factor. Right now, because of the way the displays are set up and the optics are set up, it needs to be, or we haven't been able to shrink it to a place where it's socially acceptable form factor.
Right. Adam, I thought it was interesting reading about HoloLens 2 recently that the Microsoft designers were saying that they shouldn't be guided by fashion, that this is technology, and this is... And that this is something they want an alien species to be able to visit the Earth, see this thing, and understand what it was being used for. And that's why they're focusing on enterprise, because they just don't want to deal with this as a fashion statement. I like that idea. I'm like, yeah, to heck with what people think.
Yeah, I think it's too early to worry about fashion, certainly, but I think it's important for the longer-term adoption of something like this. I really don't see a lot of people getting excited about wearing this all the time if it doesn't look good, if it's not comfortable, things like that. And then I was thinking about your comment about why would you ever need augmented reality, and I thought that was interesting because I'd never heard anyone make that argument before. I think there's a lot of human connection that happens between people when they can see each other's eyes. And to take that away actually would be a pretty detrimental experience.
Maybe so, but I could represent with great big Disney princess eyes on the outside of the headset what my eyes are actually doing, and on the other side I'm seeing video pass through with very low latency and perhaps some enhancements. I mean, I might not want to go back to these primitive transparent glasses.
All right, I'll throw one more at you, and that is the effects of light on our circadian rhythms and the damage that might do long term to only be looking at displays. Instead, I mean, maybe with super high quality displays, OLED, that sort of technology, you might be able to do that, but there's a lot of research now for that.
But think what you do with the homeless problem. You can just make it disappear. And if we're on a dystopian planet with 130-degree baked clay, it can look like a paradisiacal garden all the time. This is a way to check out from reality without having to deal with it.
Okay. Well, it's interesting you're talking about enterprise applications, and this is essentially what Google decided to do with Glass. They said, okay, well, maybe this is not going to work out for the general population, but we're going to focus on some enterprise applications for this, right? Now, there are also some technical advantages, right, to not having to recreate the entire VR experience on a headset, right? When you have the whole world and you are superimposing information. There are some technical advantages in terms of field of view of the headset and things like that. And can you talk a little bit about some of those things from your experience, Todd?
I'll let you guys probably actually
maybe pose some of the technical challenges there with AR glasses. So imagine you're wearing AR glasses walking outdoors, right? Projecting something against sunlight, that's quite a challenge for the displays and optics that we have with glasses. But certainly, like in terms of field of view, if you had like waveguides, like what the Magic Leap presentation showed, you could like focus and have augmentations only in certain part of your viewport, which is much easier in AR compared to what you can do with VR. Because VR, you need to really recreate the environment either through mapping or through see-through or through pass-through, which is not a challenge in AR.
Right.
So I think there's a twofold advantage of having these glasses, but there are also downsides of right now maybe it's only restricted for indoor experiences.
Right. Yeah. So maybe a different set of challenges. They're difficult and different in some ways and others. So very good. Very good. Adam, I was hoping you could talk a little bit about some of your experience, working with these technologies at GM. Can you talk a little bit about some of the work that you've done?
Sure. I'll talk about one thing that actually was a limitation of augmented reality, a project that I was interested in pursuing but kind of got stuck on. And that's, we had this idea. So I work in the manufacturing side of General Motors, and we had this great idea to use a HoloLens type device to visualize information about the machinery in a manufacturing plant. But one of the big problems is unless you have some sort of pre-mapped environment, then you can't really get extra information about the system. And so I think that kind of extends to the outside world too. If you go beyond a controlled environment like a plant, then you don't have an idea of that thing is an entity that this device knows about and can provide more information about. So I've actually thought a lot, and that's why my team at GM started exploring more computer vision with deep learning, because understanding the environment around you is so critical. So that's something that kind of took me in an unexpected direction. When I first started working with HoloLens, I thought this was this great thing. We could show all sorts of cool, pop-ups and, information about everything we're looking at, but you really need a fundamental understanding of that environment before you can even do that.
Right.
So that's one thing. And then otherwise, at General Motors, we built this prototype of a collaborative experience. We just did a little mechanic shop. It was a really simple, we would diagnose a problem, and then two people could be in there talking about it together and then fix the problem. That's kind of what we've done so far on my team with virtual reality. I should have clarified, that was a purely virtual reality experience. The idea would be that multiple people would be sharing a space and working on a problem that would be difficult to discuss over the phone, something like that.
Right. Yeah. No, very, very exciting, very exciting. So you're talking about this experience of, again, being able to understand your environment and be able to project information where it's supposed to be. So this brings me to the question of for example, latency that you have potentially with these kinds of devices, and also what could we do, right, if we had just a lot of bandwidth available to us, perhaps even in a wireless type of setting. What are the kinds of experiences that we can unlock, right, with that package that we cannot offer today?
So, I'll say one quick thing that's kind of maybe you wouldn't think of this, but it's a very simple scenario. You go to someone's office, you have someone else's office. Maybe I go to, a supplier, a part supplier or something, and we want to discuss something in virtual reality. I might not be able to connect to their network, but if we have high bandwidth internet that's already in the device, I don't have to worry about the friction of the network that we're in. Or if we're at a hotel or at a conference or something like that, you can really unlock a lot of things and communicate between devices without having to worry about hopping on the guest network that's unsecured. All these different things that are problems right now.
Right.
Yeah, I'd like to make a tie-in here to John Smee's excellent presentation, the keynote this afternoon. He had in mind different levels of access to data and where the computation is happening. He talked about a data center well back from the device where large data sets could be located and heavy computation could be done. Then some edge computing very close to the device, but not on the device, still wirelessly connected. And then computation being done on the device. And Edison, when you talk about latency, of course, latency matters on the device itself. If you're simply rendering some game virtual reality environment, then the motion to photons latency matters a great deal. And what we've learned in VR and AR is that needs to be down below about 15, 20 milliseconds. But if you want to interact, as Adam was saying, with a conversation that you're having, that can't be done on your device only. So that ought to be done in the edge if the interaction is local. But it has to be done more at the data center level if the interaction is across town or across the continent. And at some point, the speed of light becomes your worst enemy and causing some friction in the interaction that makes it less than natural.
Right.
So I'm kind of excited about local collaborative XR, where you could be playing a game, you could be experiencing something together, maybe doing virtual time travel together, where the interactions are very natural because it's all very low latency happening in the edge or on the device itself. I'm more worried about these kinds of tapping into a network, the Wild West network, with all of these various switches and nodes and uncontrolled latencies from end to end. I'm worried there that the latencies that we'd want, say sub 10 milliseconds, because that adds to the other latencies, right? Would be very far off indeed.
That's right. No.
So latency is very important when you are interacting with a virtual asset, say you're with AR glasses. Let's say there's a Pokemon here. I'm going to tickle it and I wanted to see it smiling in your end report. I think going over public internet is not going to work for that. So maybe we should also consider technologies like peer-to-peer networking there, where the state is stored on one device and shared across. Edge is a challenging problem for most of the companies right now. A lot of the compute is on the data centers, and trying to move it to the edge would require restructuring of the existing network topology.
Right. The whole idea was that we moved it from the device to the data centers, and then moving it back is a real
There's
heavy
quite
lift.
a bit of inertia there.
Right.
Yeah.
But it's interesting that the HoloLens. I mean, it's a completely self-contained unit right now, right? So there is no subsystem that is on the cloud, on Azure or anything like that they offer.
No, but it is connected.
It can be connected, right?
It can be connected.
But I think that they have architected the system. They're already architecting the system such that there's a lot of computational power within the device. I think anticipating a lot of these opportunities, right? Yeah.
And they do support what's called as Azure spatial computing now.
Right.
So spatial anchors. So you can actually persist virtual objects and then have that rendered from your phone, and then you're able to see it on your glasses. So they do have cloud support for it.
Yeah.
Those anchors, though, aren't persistent in the sense that if the environment changes, if the visual features in the environment changes, they can't remain.
Exactly. So these are using visual features.
Which
for
is
real
why I
life.
think, if you're going to bury something in your backyard, you better not trust in the Azure anchors. Because if it snows, then who knows where it is, right?
Yeah. I think what we should do is we should open up for some questions. I see that we're already past 5 o'clock, so...
yeah, if we have very few questions, we can just adjourn.
We can just wrap it up right here. No, but I'm sure there are some questions, a couple of questions maybe. Yes?
So do you see this possibly transitioning to maybe a theme park type of setup when you were talking about your AR type experience where you're kind of applying a filter over the world. So you would know exactly the theme park layout because you would have designed it and created it.
Yeah, I wouldn't mind that, but it's basically already been done indoors. The Void and others have experimented with this kind of extended reality indoors with a really controlled environment. Actually, even tactile stuff. You reach out and touch buttons that are actually just painted on cardboard virtually. I like the idea of having a fleet of drones that follow you around and create this real time, you know, and so they're out in front of you mapping, and you're just walking, so that you're not confined to any lesser environment. This is really boundless exploration. Now that's kind of weird. Batteries are going to run out on the drones, and then what? You run out of virtual world. But I don't like this being any more. Once we break free from living rooms, I don't want to be trapped in a football stadium. I want to just be able to walk and walk extensively.
All right. One more question? No more questions? Okay. Oh, we have one question. Constantine, yes.
I'm curious about what your feeling is with the lesson that the industry took from Google Glass. And I mean, it's kind of the hope for why there is now going to be, perhaps this is the way forward, or not lightweight is the way forward, or what's the lesson for us to take away from something that seemed ready? Was it the invasiveness that broke it, or what?
I have a thought on that. The question, in case people couldn't hear, was what happened with Google Glass, basically, and what can we learn from that, the fact that it kind of disappeared. Personally, I think it was a social issue. It seemed like a lot of people got really upset about the idea of people wearing a camera on their face, that it wasn't clear that they were recording. Of course, I think that people's opinions on that are changing over time. It seems like the younger generations are much more comfortable with being recorded, and they don't seem to care about privacy. So that may change over time. But yeah, in terms of technology, it seems like Google Glass was actually a really interesting first step. It was limited in what it could do, but it was, so is my watch. But that shouldn't stop it from being a successful technology. I don't know if you guys agree.
To me, I think the lack of very compelling experiences with glass was probably the major killer for it, or probably killed it. And also the price point. I mean, for me to buy an accessory which is that expensive, at the same time also have my phone around, doesn't actually justify such an investment. So HoloLens is a great example where it's completely untethered on one unit. So maybe this is the way forward, but I'm really hoping for something that's even more socially acceptable in terms of form factor.
I see, Constantine, in the HoloLens debut the last couple of weeks, a lot of lessons learned from glass. They didn't have really beautiful models showing this off and trying to persuade the public that you could wear this in public. They are saying this is for enterprise, it's $3,500, and we're not trying to make a fashion statement. And so don't kick us out of the bar,
Yeah.
because we've got this, and we wouldn't wear it to the bar, right? And I think those were valuable lessons learned.
They came from different perspectives, too, right? I think Google Glass was initially portrayed as an accessory that you'd incorporate into your everyday life, whereas, this whole space of VR didn't come from this perspective of an accessory. It's a whole experience, and it's becoming lighter and lighter and lighter to the point where we got to this. It's still not something you would wear every day and be completely comfortable, but it's getting there. So it's just very interesting how these two worlds are sort of coming together. So. All right, let's thank our wonderful panelists. And this is the end of our show here. We have a reception at 5 o'clock, which is now. But before we wrap it up completely, I would like to again thank our sponsors for today's Texas Wireless Summit. So Norton Rose Fulbright and Holland and Knight. Thank you very much to RCR Wireless and the IEEE Communication Society, the Central Texas chapter, and of course UT Austin and the Cockrell School of Engineering, and here the Department of Electrical and Computer Engineering, And I also would like to acknowledge all the help that we got from the WNCG staff, Karen and Jamie and Apple and everybody who made this event a great success today. I hope you all enjoyed, and I'll see you out there. We can chat some more. And thanks for coming, and have a safe trip back.